There is a rock out there, somewhere in the black cathedral of space, that carries on its scarred surface the entire trajectory of life on Earth. Not because it struck our world, but because it almost didn't. 66 million years ago, give or take a Thursday, a piece of ancient debris roughly 11 kilometers wide, a mountain set adrift since the infancy of the solar system, was falling toward a pale blue planet that did not yet know the word extinction. It had no malice. It had no purpose. It was simply obeying gravity, that most democratic of forces which treats a grain of sand and a civilization with precisely the same indifference. You know this story, or you believe you do. The rock hits, the dinosaurs die, the mammals rise. Humans eventually appear, invent language, build cities, and make documentary films about what came before them. It is a neat arc, tragic, triumphant, almost biblical in its symmetry, and it is, in the most generous interpretation, only half true. Before we unspool the thread of a world where that rock missed its appointment with the Yucatan Peninsula, we must first correct a lie that has been told so often it has calcified into common knowledge. The lie is this: that the dinosaurs were failures, that they were evolutionary dead ends, slow, stupid, cold-blooded relics lumbering toward an inevitable extinction, and that the asteroid merely accelerated a process already underway. Popular culture has been extraordinarily generous with this narrative. It appears in children's books, in museum plaques, in the casual shorthand of people who use the word dinosaur to mean something outdated and doomed. The truth is so much stranger and so much more unsettling. The non-avian dinosaurs dominated terrestrial ecosystems for approximately 165 million years. To place that number in perspective, the entire history of the genus Homo, every tool, every fire, every war, every poem, occupies roughly 3 million years. The dinosaurs reigned for 55 times longer. They survived the Triassic-Jurassic extinction that wiped out most of their competitors. They endured continental rifts that tore Pangaea apart like wet bread. They weathered volcanic winters, ocean anoxia events, and fluctuations in atmospheric chemistry that would have suffocated most modern mammals. They did not merely persist, they thrived. They diversified into thousands of species across every landmass on Earth, from the polar forests of Cretaceous Antarctica to the arid interiors of what would become the Sahara. They were not cold-blooded. Decades of paleophysiological research, bone histology studies by Armand de Riclès, isotopic analyses by Robert Eagle and colleagues, have demonstrated that many dinosaur lineages were endothermic or mesothermic, maintaining elevated body temperatures through metabolic heat production. The giant sauropods likely achieved a form of homeothermy through sheer mass, a phenomenon called gigantothermy, where the ratio of volume to surface area is so extreme that the body retains heat almost passively. They were not slow. Biomechanical analyses of theropod trackways suggest sustained speeds that would outpace most modern terrestrial predators. They were not stupid. The encephalization quotients of troodontids and dromaeosaurids placed them within the range of modern birds, which, one must remember, are themselves dinosaurs, the only lineage that slipped through the bottleneck of the Cretaceous-Paleogene boundary. The asteroid did not end an era of decline. It interrupted a dynasty at its zenith. And this is what makes the question so vertiginous. What if it hadn't? Let us be precise about the mechanics. The Chicxulub impactor, named for the coastal town in Mexico's Yucatan Peninsula near the center of its burial crater, struck the Earth at approximately 20 kilometers per second. That is roughly 60 times the speed of sound. The energy released upon impact has been estimated at around 100 trillion tons of TNT. 10 billion times the yield of the Hiroshima bomb. The collision vaporized the impactor itself, along with a vast volume of the carbonate and anhydrite-rich seafloor beneath it. This is a critical detail, often overlooked. The specific geology of the impact site, shallow tropical sea, sulfur-rich sedimentary rock, dramatically amplified the catastrophe. The vaporized sulfates generated sulfuric acid aerosols that blocked sunlight for years. The carbonates released enough carbon dioxide to trigger a greenhouse rebound after the initial cooling. Had the asteroid struck deep ocean basalt or a granitic continental interior, the extinction might have been significantly less severe. And herein lies the branching point. Not merely whether the rock arrives, but where and how it arrives. Imagine then a universe almost identical to ours. Same solar system, same Oort cloud debris, same gravitational choreography of Jupiter and Saturn nudging ancient rubble inward toward the inner planets. But in this universe, the geometry is fractionally different. Perhaps the asteroid's orbit was perturbed by a marginally different encounter with a Jovian resonance 3 million years earlier. Perhaps it arrived 6 hours later, striking the deep Pacific rather than the shallow Yucatan shelf. Perhaps it fragmented during atmospheric entry, not into harmless dust, but into several large bolides, each devastating but none delivering the singular, concentrated blow that made Chicxulub an extinction-level event. Or perhaps, most simply, it missed. The rock sails past. It crosses Earth's orbit a mere 4 hours after the planet has already moved on, a cosmic near-miss of the kind that happens, in geological terms, with some regularity. The night sky over the late Cretaceous flickers briefly as the interloper catches the sun's light, and then it is gone, swallowed by the outer dark, destined to orbit in silence for another 100 million years, until some other gravitational accident gives it a second chance at significance. On the ground, nothing changes. A Tyrannosaurus rex, in what will one day be Montana, lifts its massive skull from a carcass of Edmontosaurus, scanning the tree line with eyes that can resolve detail at distances most mammals will never match. In the forests of what will become India, a mother Isis, a titanosaur, tends to a clutch of eggs half buried in volcanic soil, still warm from the Deccan traps. A flood basalt province that has been hemorrhaging lava for nearly 1 million years. The Deccan eruptions are real, they are severe, and they are, on their own, survivable. A 2020 study published in Science by Pincelli Hull and colleagues demonstrated that while the Deccan volcanism caused significant environmental stress, it was the asteroid impact that pushed ecosystems past the tipping point. Remove the asteroid, and the Deccan traps become a crisis, not an apocalypse. Life bends, it does not break. The Cretaceous continues. And so begins a story that no human will ever live to tell, because in this story, there are no humans. So, before you allow yourself to settle fully into this journey, take a moment to like and subscribe. But only if what you are hearing genuinely compels you. And if it does, share where you are watching from and what time it is in your corner of the world. Because the story we are about to tell stretches across 66 million years and every continent on Earth. And it begins with the simplest and most terrifying of premises. Nothing happened. The rock missed. The world moved on. And everything was different. To understand what was saved, one must first understand what was avoided. And to understand what was avoided, one must be willing to stare directly into the anatomy of an apocalypse. The Chicxulub impact, the one that happened in our timeline, the one that did not happen in this alternate telling, was not a single catastrophe. It was a cascade, a sequence of interlocking devastations, each one sufficient to reshape the biosphere, all of them arriving within hours, days and years of one another, stacking atop each other like waves in a storm surge that never recedes. Let us reconstruct it, not to mourn, but to measure precisely what the living world, in our divergent timeline, was spared. The first second is almost incomprehensible. The asteroid, 11 kilometers of carbonaceous chondrite and nickel iron, older than the Earth itself, enters the atmosphere at a shallow angle, roughly 60 degrees from horizontal. According to modelling work by Gareth Collins and colleagues at Imperial College London, the atmospheric transit takes less than 2 seconds. There is no time for the air to move aside. It is compressed, superheated, and converted into a column of plasma reaching temperatures exceeding 10,000 degrees Celsius. The light alone, the sheer electromagnetic radiation of the entry, would have ignited forests within a radius of perhaps 1,500 kilometers. Animals looking toward the horizon in what is now the Gulf of Mexico would have been blinded instantly, their retinas seared by a flash brighter than 1,000 suns. Then comes the contact. The impactor strikes the shallow continental shelf at roughly 20 kilometers per second. In the first tenth of a second, it penetrates the entire water column, perhaps 200 meters deep at that point, and buries itself into the seafloor. The kinetic energy converts to thermal energy so rapidly that the rock does not shatter. It vaporizes along with cubic kilometers of limestone, gypsum, and seawater. A transient cavity opens in the Earth's crust, a hole roughly 100 kilometers across and 30 kilometers deep. For a few terrible seconds, the mantle itself is exposed to open air. Then the walls collapse inward, the rebound peak rises, and the final crater settles into a ring structure approximately 180 kilometers in diameter, now buried beneath the Yucatan Peninsula and partially beneath the Gulf of Mexico. But the crater is almost an afterthought. The true killing mechanisms are atmospheric and oceanic. The ejector, billions of tons of molten rock and vaporized sediment, is launched on ballistic trajectories that carry it beyond the atmosphere. Within an hour, this material re-enters the atmosphere across the entire planet, heating the upper air to oven-like temperatures in a phenomenon Sean Gulick and Joanna Morgan described as a broiler effect. Global wildfires ignite not from direct flame, but from the infrared radiation of re-entering debris. The charcoal layer found at the Cretaceous-Paleogene boundary in sediments from New Zealand to Denmark to the American Midwest is the chemical signature of a world that burned simultaneously on every continent. Then comes the darkness. The sulfuric acid aerosols generated from the vaporized anhydrite, calcium sulfate, rise into the stratosphere and remain there for years, perhaps a decade. Sunlight drops to a fraction of its normal intensity. Photosynthesis collapses. The base of nearly every terrestrial and marine food chain is severed. Temperatures plummet. A study by Julia Brugger and colleagues, published in Geophysical Research Letters in 2017, modelled a global average temperature drop of approximately 26 degrees Celsius in the first 3 years. An impact winter that would have frozen the surface waters of tropical oceans. The organisms that survived, small, burrowing, cold-tolerant, capable of subsisting on detritus and decay, were not the fittest in any traditional sense. They were the luckiest. They happened to occupy ecological niches that were, by sheer accident, pre-adapted to survive a world without sunlight. This is what the late Cretaceous was spared, in the timeline where the rock sailed past. Now, imagine the morning after the non-event. There is no morning after, of course. There is no event to follow. There is only Tuesday becoming Wednesday. the Maastrichtian age continuing its slow geological heartbeat, the seasons turning, the Deccan traps still belching sulfur dioxide and carbon dioxide into the Indian sky. The Deccan eruptions deserve a closer examination because they are often cast as a co-conspirator in the extinction narrative, sometimes even as the primary culprit. This is not quite right. The Deccan Traps, a flood basalt province in west-central India, erupted in pulses over approximately 1 million years, beginning before the Chicxulub impact and continuing after it. The total volume of lava produced was staggering. Estimates range from 1 to 2 million cubic kilometers, enough to bury the entire state of Texas under nearly 2 kilometers of basalt. The associated gas emissions, carbon dioxide, sulfur dioxide, mercury, halogens, were significant enough to cause measurable ecological stress. Ocean acidification increased, global temperatures fluctuated. Some species experienced range contractions. But, and this is the critical distinction, the biotic response to the Deccan eruptions as reconstructed from the fossil record was one of stress and partial recovery, not collapse. Work by Blair Schoen and colleagues at Princeton using high-precision uranium-lead geochronology showed that the most intense pulse of Deccan volcanism may have slightly preceded the asteroid impact, and yet the mass extinction signal in the fossil record is sharply concentrated at the impact boundary itself. The volcanism was a fever. The asteroid was a bullet. Remove the bullet, and the patient survives the fever. In this alternate timeline, the Deccan eruptions continue for another several 100,000 years. They cause regional devastation across the Indian subcontinent. Vast tracts of forest destroyed, rivers of basalt reshaping drainage systems, local extinctions of species unable to migrate away from the lava fields. But globally, the biosphere absorbs the shock. Carbon dioxide levels rise, contributing to the already warm greenhouse climate of the late Cretaceous. Sea levels, already high, may tick upward another few meters as thermal expansion warms the oceans. The Western Interior Seaway, that vast shallow sea that, in the late Cretaceous, bisected North America from the Gulf of Mexico to the Arctic, persists, perhaps even expands slightly. And the dinosaurs. They do what they have done for 165 million years. They adapt. The great herds of ceratopsians, Triceratops, Torosaurus, Pachyrhinosaurus, continue to crop the low vegetation of the North American coastal plains. The hadrosaurs, duck-billed dinosaurs with complex dental batteries capable of processing tough plant material, continue their slow ecological conquest of the flowering plant world. The angiosperms, those evolutionary newcomers that had been steadily diversifying through the Cretaceous, keep spreading, and the herbivorous dinosaurs co-evolve with them, just as they have been doing for 30 million years already. In the shadows, always in the shadows, the mammals wait. Small, warm-blooded, mostly nocturnal, they occupy the interstices of the dinosaurian world. Insectivores, seed-eaters, perhaps a few omnivorous forms the size of a modern badger, but no larger. The ecological ceiling imposed by dinosaur dominance is absolute. In our timeline, the removal of that ceiling, the extinction of all non-avian dinosaurs, triggered the most explosive adaptive radiation in mammalian history. Within 10 million years of the asteroid impact, mammals had diversified into bats, whales, primates, ungulates, and carnivores. Every ecological role vacated by a dinosaur was filled by a mammal. In this timeline, the ceiling holds. The mammals remain small, the shadows remain full, and the world belongs, as it has belonged for eons, to the dinosaurs. But the world is not static. The Cretaceous will end, not with a bang, but with a slow geological exhalation. Continents will drift, oceans will open and close, climates will swing from greenhouse to icehouse and back again. And the dinosaurs, those magnificent inheritors of a spared world, will face challenges that no asteroid could replicate. Challenges written not in the language of catastrophe, but in the patient, pitiless grammar of time. The Maastrichtian gives way to the Danian. The Paleocene begins. And 66 million years of unwritten history stretches forward like an ocean without a far shore. The story, in truth, is only beginning. To project forward, one must first stand still. Before the clock of this alternate history begins to tick, before continents drift and climates swing and lineages diverge into forms no human eye has ever seen, one must know precisely what the world looked like at the moment of divergence. Not the caricature, not the swamp and volcano diorama of a mid-century museum, but the real late Cretaceous in all its alien beauty. Stand, if you will, on the western shore of the great inland sea that divides North America. It is approximately 66 million years before the present. The air is warm, startlingly warm by modern standards. Global average temperatures hover around 23 to 25 degrees Celsius, roughly 8 to 10 degrees warmer than today. There are no permanent ice caps. Not on Antarctica, which sits closer to its current position, but is cloaked in temperate forest. Southern beach, podocarp conifers, ferns taller than a man. Not on the Arctic, where the mean annual temperature is perhaps 10 to 12 degrees Celsius. Cool enough for frost, but not for glaciation. The planet is in a greenhouse state, driven by atmospheric carbon dioxide concentrations, estimated between 1,000 and 1,400 parts per million, roughly 3 to 4 times the modern pre-industrial level. The warmth is not merely tropical, it is global. The temperature gradient between equator and pole is dramatically flatter than today. This has profound consequences for weather. Without steep thermal gradients, the great atmospheric circulation cells that drive modern jet streams and storm tracks are weaker, broader, more diffuse. Hurricanes may be more frequent in the warm, shallow seas, but the ferocious mid-latitude cyclones that define modern winters are attenuated. Seasons exist, particularly at higher latitudes, but they are gentler. The difference between a warm summer and a cool winter, not between blistering heat and killing frost. The geography is almost unrecognizable. The Atlantic Ocean is narrower. South America and Africa are closer, connected by island chains that permit sporadic faunal exchange. India is an island continent, racing northward through the Tethys Sea toward its eventual collision with Asia, carrying with it a cargo of unique titanosaurs, abelisaurid predators, and an ecosystem isolated by millions of years of ocean. Australia and Antarctica are still connected or only recently separated, sharing fauna across a land bridge that will soon be severed by the opening of the Tasman Gateway. Europe is an archipelago, a scattering of limestone islands in a warm, shallow sea, each one a miniature evolutionary laboratory producing dwarf dinosaurs adapted to island life. The famous dwarf Titanosaur Magyarosaurus of Hatzeg Island, Romania, described by Franz Nopser in the early 20th century, was no larger than a horse, a full-sized sauropod lineage compressed by the ecological constraints of limited island territory, a textbook case of insular dwarfism. And the Western Interior Seaway, that extraordinary body of water that in the late Cretaceous stretched from the Gulf of Mexico to the Arctic Ocean, splitting North America into two landmasses called Laramidia to the west and Appalachia to the east, is in its final stages. It is shallow, warm, rich with life. Mosasaurs patrol its depths. Vast colonies of ammonites spiral through its waters and along its muddy shores, Great herds of hadrosaurs and ceratopsians feed on the lush vegetation that thrives in the humid coastal climate. The vegetation itself is in the midst of a revolution, slow by human standards, explosive by geological ones. The angiosperms, the flowering plants, first appeared in the fossil record during the early Cretaceous, perhaps 130 million years ago. By the late Cretaceous, they have diversified enormously, conquering lowland habitats and riparian corridors, though they have not yet displaced the conifers and ferns from the uplands and the forest canopy. The world is a patchwork. Dense Araucarian and podocarp forests on the highlands, mixed angiosperm conifer woodlands in the mid-elevations, and broad coastal plains dominated by flowering shrubs, early palms and water-loving plants. The air is thick with the scent of resin and pollen. Insects, beetles, wasps, ants, flies, and the newly diversifying lepidopterans are everywhere, locked in co-evolutionary spirals with the flowers that feed them. It is into this world that we must place the players of our alternate history. The megafauna are staggering. In Laramidia, Tyrannosaurus rex occupies the apex predator niche, a 12-meter, 8-ton theropod with a bite force estimated by Gregory Erickson and colleagues at approximately 57,000 newtons, the strongest of any terrestrial animal in the known fossil record. Its serrated teeth are not blades but crushing instruments, capable of pulverizing bone, a feeding strategy confirmed by coprolite analysis showing fragmented bone from ceratopsians and hadrosaurs. It hunts, or scavenges, or likely both, across a home range that may encompass hundreds of square kilometers. Its prey is no less impressive. Triceratops horridus, perhaps the most iconic ceratopsian, weighs up to 9 tons, its massive frill and 3 horns serving functions both defensive and social, display structures for intraspecific signaling, thermal regulation, or species recognition. Edmontosaurus, a hadrosaur, moves in herds that may number in the thousands, their dental batteries, stacked rows of hundreds of tiny teeth, functioning as a single grinding surface, allowing them to process plant material with an efficiency unmatched by any reptile before or since. In the air, Quetzalcoatlus northropi, an Azhdarchid pterosaur, soars on wings spanning 10 to 11 meters, its long, stiffened neck and dagger-like beak adapted for terrestrial stalking, picking off small dinosaurs and mammals from the ground in the manner of a monstrous stalk, a feeding ecology proposed by Mark Whitten and Darren Naish in 2008. And beneath all of this, beneath the thunder of ceratopsian herds and the shadow of pterosaur wings, the mammals endure. They are diverse in their way. The multituberculates, a spectacularly successful order that first appeared in the Jurassic, occupy rodent-like niches across the northern hemisphere, gnawing seeds and fruits with their characteristic blade-like premolars. Small marsupials and placentals, Didelphodon, Purgatorius, Zalamdalestes, hunt insects, raid nests, and scavenge scraps. A few, like Repenomamus from the earlier Cretaceous of China, had achieved modest sizes and were even capable of preying on small dinosaurs. But in the late Maastrichtian, no mammal exceeds the size of a domestic cat. The dinosaurs, with their metabolic advantages, their reproductive strategies, high egg output, rapid juvenile growth, and their sheer incumbency, hold every large-bodied niche firmly closed. This is not a world waiting to be replaced. It is a world in full bloom. There is a temptation, when constructing alternate histories, to begin with the assumption that the world as it was constituted some kind of preliminary draft, a rough sketch waiting for the real story of mammals, primates, and humans to begin. This is not merely wrong, it is a form of narrative narcissism. The late Cretaceous was not a prelude. It was a climax, one of many that the biosphere has achieved in its 4 billion-year history, and one that, in our timeline, was terminated not by internal failure but by external violence, by a rock from space that cared nothing for the elegance of what it destroyed. In this alternate timeline, the elegance continues. The Maastrichtian slides into the Daanian. The Paleocene opens without its defining catastrophe, and the great greenhouse world of the late Mesozoic, far from collapsing, begins to evolve. The garden is unbroken. The gardeners, scaled, feathered, and enormous, remain at their posts. And the 66-million-year experiment that our timeline never ran is about to begin. Every great drama has its minor characters, the ones who stand at the edges of the stage, half-lit, easily overlooked, and yet without whom the entire plot would unravel. The late Cretaceous is no different. While the colossal tyrannosaurs and the armored ceratopsians command the eye, the true seeds of the next 66 million years lie elsewhere. In creatures small enough to hold in your hand, quiet enough to escape the notice of any predator, and flexible enough to inherit whatever world the future decides to build. Let us turn the camera away from the giants. Let us look at the hidden players. Begin with the troodontids. Troodon, or more precisely, the complex of species once grouped under that name before taxonomic revisions scattered them across several genera, was a small theropod, perhaps 2 meters long and weighing no more than 50 kilograms. It was, by the standards of its time, unremarkable in size. But its brain was not. The encephalization quotient of troodontids, the ratio of brain mass to body mass, adjusted for allometric scaling, was the highest of any known non-avian dinosaur, and comparable to that of modern emus and some corvids. The implications are significant. Dale Russell, the Canadian paleontologist who in 1982 proposed the infamous dinosauroid thought experiment, was wrong about the shape that intelligence might take. His bipedal humanoid extrapolation was a projection of primate anatomy onto a fundamentally different body plan, a fallacy we will address in detail later. But he was not wrong about the substrate. Troodontids possessed large, forward-facing eyes with excellent stereoscopic vision, likely adapted for hunting in low-light conditions. Their sickle-clawed feet, a hallmark of the Deinonychosaur clade, suggest active, agile predation. Their relatively large brains hint at complex behavioral repertoires, perhaps coordinated hunting, perhaps sophisticated parental care, perhaps problem-solving abilities that we, from our 66 million year remove, can only infer from comparative anatomy. In a world where the asteroid does not strike, the troodontids do not disappear. They are small, they are adaptable. They are, in the language of ecology, generalists, capable of occupying a range of niches, feeding on a variety of prey, and adjusting their behavior to shifting conditions. These are precisely the traits that fuel adaptive radiation when opportunity arises. Not catastrophic opportunity, as in our timeline, but the slow, grinding opportunity of environmental change, continental drift, and competitive displacement over millions of years. Now consider the dromaeosaurids, the raptors, in popular parlance, though the word has been so thoroughly colonized by Jurassic Park that it has almost lost its scientific meaning. The dromaeosaurid family in the late Cretaceous was remarkably diverse. At one end of the spectrum stood Deinonychus and its relatives, mid-sized pack hunters with the sickle claw, the stiffened tail for balance during high-speed turns, and the large brain that suggests coordinated group behavior. At the other end stood the microraptorines, tiny four-winged gliders from the forests of Cretaceous China, blurring the boundary between non-avian dinosaurs and birds so thoroughly that their classification sparked decades of debate. Between them lay a continuum of body plans, ecological strategies, and evolutionary potential. The dromaeosaurids were not a single type. They were a family of possibilities. And then there are the birds. This is perhaps the most important correction to make, because it is the one most frequently misunderstood. The birds did not replace the dinosaurs. The birds are dinosaurs. Every sparrow, every eagle, every penguin is a living theropod dinosaur, a member of the clade Maniraptora, nested within the same evolutionary tree that produced Velociraptor and Tyrannosaurus. In our timeline, the avian dinosaurs were the sole surviving lineage of the Dinosauria, the only branch that threaded the needle of the end Cretaceous extinction. In this alternate timeline where the extinction does not occur, the birds still exist. But they exist alongside their non-avian relatives, competing with them, diverging from them, and filling ecological niches that in our world they eventually monopolized. The late Cretaceous already hosted a remarkable diversity of birds. The Enantiornithes, the opposite birds, named for a reversed articulation in their shoulder joint, were the dominant avian group, occupying arboreal niches across every continent. They had teeth, they had clawed wings. They were superb flyers, filling ecological roles analogous to modern songbirds, woodpeckers, and raptorial hawks. In our timeline, they went extinct at the Cretaceous-Paleogene boundary, completely. Not a single enantiornithine lineage survived. Their extinction opened the door for the neornithes, the modern bird clade, the one that includes every living bird species, to radiate into the vast ecological space left behind. In this alternate timeline, the enantiornithines survive. And this changes the trajectory of avian evolution profoundly. The modern bird radiation, the explosion of passerines, raptors, waterfowl and shorebirds that defines the avian world we know, is suppressed, or at least dramatically delayed and altered. Instead, the enantiornithes continue to dominate arboreal and aerial niches, their toothed beaks and clawed wings persisting as competitive advantages in a world where they do not need to yield to the toothless, claw-reduced neornithes. The birds of this alternate present, 66 million years hence, may be almost unrecognizable to a modern ornithologist. Not because they have become radically alien, but because the lineages we consider normal never had the ecological opportunity to become dominant. Below the dinosaurs, below the birds, another group persists in quiet significance, the crocodilomorphs. Modern crocodilians, alligators, crocodiles, gharials, are a pale shadow of Mesozoic crocodilomorph diversity. In the Cretaceous, the group included fully terrestrial forms like the notosuchians, small, agile predators and herbivores that filled ecological roles on land, more typically associated with mammals. Samosuchus, a stubby, armored herbivore from the late Cretaceous of Madagascar, looked more like an armadillo than a crocodile. Ararippasuchus from South America and Africa was a long-legged, nimble terrestrial predator sometimes called the dog croc for its cursorial build. These forms, largely wiped out or marginalized in our timeline as mammals expanded, would persist in the alternate history, continuing to compete with small theropods and mammals for terrestrial niches, maintaining a presence on land that their modern descendants have largely abandoned. And finally, consider the pterosaurs. By the late Cretaceous, the pterosaurs were in a state of apparent decline. Their diversity had dropped considerably from the Jurassic peak, and the remaining lineages were dominated by the Ajdarchids, those enormous terrestrial stalkers with wingspans exceeding 10 meters. Some paleontologists, notably David Unwin, have argued that the pterosaurs were being competitively displaced by birds even before the asteroid struck. Others, including Mark Whitten, have countered that the Ajdarchids occupied a fundamentally different ecological niche. Large-bodied terrestrial foragers rather than aerial competitors, and that pterosaur and bird diversity were not directly inversely correlated. In this alternate timeline, the question becomes a 66 million-year experiment. Can the pterosaurs persist alongside an ever-diversifying avian radiation, or are they doomed by competitive exclusion regardless of any asteroid? The answer, as with most things in evolutionary biology, is likely not a clean binary. Some pterosaur lineages probably succumb to bird competition within the first 10 or 20 million years. Others, particularly the giant Ajdarchids, which have no avian analogue, may persist far longer, perhaps evolving into even more specialized terrestrial forms, their wings reduced, their legs lengthened, filling niches that in our timeline were eventually occupied by terror birds and ground-dwelling raptors. These, then, are the hidden players, the big-brained troodontids, the versatile dromaeosaurids, the toothed enantiornithine birds, the terrestrial crocodilomorphs, the giant pterosaurs, and, always, the tiny, waiting mammals. Each carries within its genome a library of potential futures. Each is a thread in a tapestry that, in our timeline, was shredded by an accident of celestial mechanics. In this timeline, the tapestry holds, the threads remain intact, and the weaving continues. The clock begins to move, not in the sudden, violent lurch of catastrophe. There is no catastrophe here, remember, but in the slow, immense rhythm of geological time, a rhythm measured not in years or centuries, but in millions of years, in the patient grinding of tectonic plates and the invisible drift of atmospheric chemistry. The first great test arrives approximately 10 million years after the divergence point. It is called, in our timeline, the Paleocene-Eocene thermal maximum, the PETM. And it is one of the most dramatic climate events of the entire Cenozoic era. It will happen here too because it has nothing to do with asteroids. It is written into the carbon cycle of the planet itself. Approximately 56 million years ago, a massive pulse of carbon, perhaps 5 trillion metric tons, though estimates vary, enters the atmosphere over a geologically brief period of perhaps 20,000 years. The source remains debated. Volcanic outgassing from the nascent North Atlantic igneous province as Greenland rifts away from Europe. The destabilization of methane clathrates on the continental shelves, the thermal metamorphism of organic-rich sediments by igneous intrusions. Or, most likely, some cascading combination of all three. The effect is unambiguous. Global temperatures spike by 5 to 8 degrees Celsius on top of an already warm baseline. The deep oceans warm by 4 to 5 degrees. The Arctic, already ice-free, becomes subtropical. Crocodilian fossils and palm pollen are found in sediments from Ellesmere Island, above the Arctic Circle, in our timeline. The same will be true here, but here the organisms facing this furnace are different. In our timeline, the PETM was navigated by early mammals, the ancestors of modern horses, primates and carnivores, many of which responded by shrinking in body size, a phenomenon documented by Philip Gingerich and others, and consistent with Bergmann's rule applied in reverse. In warmer climates, smaller bodies dissipate heat more efficiently. The mammalian world of the Paleocene was still in its infancy, its lineages plastic, its body plans malleable, its ecological roles still being defined in the vast emptiness left by the dinosaur extinction. In the alternate timeline, there is no such emptiness. The dinosaurs are still here, and they must face the Eocene furnace with body plans forged in the Mesozoic. For the large-bodied forms, the sauropod descendants, the ceratopsians, the hadrosaurs, the PETM represents a thermoregulatory crisis. Large endothermic or mesothermic animals in an already warm world now face temperatures that push against the upper limits of physiological tolerance. But the dinosaurs are not without resources. Gigantothermy, that same thermal inertia that kept sauropods warm in cooler conditions, now becomes a liability. But it is a liability that can be mitigated by behavioral and anatomical adaptation. Modern elephants facing similar thermoregulatory challenges have evolved enormous ears richly vascularized for radiative cooling, mud-bathing behaviors, crepuscular and nocturnal activity patterns, and a relative reduction in body hair. There is no reason, grounded in biological principle, why large dinosaurs could not evolve analogous solutions. Expanded frills in ceratopsians repurposed as heat-dissipating surfaces, increased vascularization of cranial crests in hadrosaurs, shifts toward nocturnal or twilight activity in the largest theropods. A 2014 study by Roger Seymour in PLOS1 on sauropod cardiovascular physiology suggested that these animals already possessed sophisticated circulatory adaptations to manage blood pressure in their long necks. The same vascular architecture could be co-opted for thermoregulation under thermal stress. The smaller theropods, the dromaeosaurids, the troodontids, the early avian lineages, face a different set of pressures. For them, the PETM is less about overheating and more about ecological restructuring. The vegetation changes. In our timeline, the PETM triggered a significant turnover in plant communities. Tropical forests expanded poleward, deciduous forests retreated, and the composition of floral assemblages shifted towards species adapted to high temperature and high carbon dioxide. The same will happen here. Forests become denser, wetter, more layered. The canopy thickens. The understory darkens. For arboreal predators, the small dromaeosaurids, the enantiornithine birds, this is an opportunity. Denser forests mean more vertical habitat, more niches to partition, more prey hiding in more layers of vegetation. The selective pressure favors smaller body size, improved climbing ability, sharper low-light vision, and more sophisticated cognitive mapping of three-dimensional space. This is where the troodontid lineage begins to differentiate. In the hothouse forests of the Eocene, the descendants of the late Cretaceous troodontids split into at least two broad ecological strategies. One lineage trends larger, occupying the mid-sized predator niche on open ground, filling a role analogous to the wolves and hyenas of our Cenozoic. The other trends smaller and more arboreal, retreating into the canopy where their large eyes, binocular vision, and relatively large brains give them an advantage in the complex three-dimensional hunting environment of a multi-layered tropical forest. These arboreal troodontids, over millions of years, develop grasping forelimbs with increased manual dexterity. Not because they are trying to become intelligent, not because evolution has a direction, but because the same selective pressures that produced grasping hands in primates and raccoons and parrots operate here as well. The need to navigate branching structures, manipulate food items, and coordinate limb movement with visual input. Meanwhile, the continents are rearranging themselves. India, that wayward fragment of Gondwana, is completing its long northward journey. Sometime around 50 million years ago, the timing is imprecise, but the event is certain. It collides with the southern margin of the Asian plate. The collision is not a single moment, but a protracted process spanning millions of years, crumpling the crust upward into what will eventually become the Himalayan mountain range and the Tibetan plateau. In our timeline, this collision had profound effects on global climate. The uplift of Tibet altered atmospheric circulation patterns, strengthened the Asian monsoon system, and may have contributed to long-term global cooling by increasing silicate weathering and drawing down atmospheric carbon dioxide. The same tectonic event occurs in the alternate timeline, and its climatic consequences are identical. The Himalayas rise, the monsoons intensify, and the global carbon cycle begins, slowly, imperceptibly, to shift. The Tethys Sea, that ancient ocean that once separated the northern and southern continents, is closing. As Africa pushes northward into Europe and India docks with Asia, the Tethys narrows, its circulation patterns disrupted, its warm equatorial waters increasingly confined. This has consequences for global ocean circulation, for the distribution of marine nutrients, and for the marine reptiles and other organisms that depend on Tethyan productivity. In the alternate timeline, any marine reptile lineages that have persisted, descendants of Cretaceous freshwater or coastal forms that expanded seaward, must now contend with a shrinking ocean and shifting current patterns. On land, the great sauropod lineages face a subtler challenge. The angiosperms, which had been diversifying steadily through the Cretaceous, now accelerate their conquest. By the Eocene, flowering plants dominate most lowland and mid-elevation habitats worldwide. The conifer forests that once sustained the great titanosaur herds are retreating to higher elevations and higher latitudes. Sauropod descendants must adapt to new food sources, tougher, more chemically defended angiosperm foliage, or retreat with the conifers. Some lineages do both. The lowland sauropods over 10 million years evolve more sophisticated dental systems, perhaps convergent with the dental batteries of hadrosaurs, to process the fibrous, tannin-rich leaves of the expanding hardwood forests. The highland sauropods remain more conservative, browsing on conifers in montane refugia, their body sizes perhaps declining as cooler upland temperatures and reduced food availability impose new constraints. The world is changing, not in a single terrible afternoon, as it did in our timeline, but across millions of years, slowly enough for evolution to respond, quickly enough to demand that it does. The PETM passes. Temperatures gradually recede from their peak, though the world remains far warmer than it will be in the Pleistocene. The Eocene settles into a long, warm plateau, the last great greenhouse interval before the planetary thermostat begins to turn downward, and in the forests and plains and shallow seas of this warmer world, the dinosaurs, adapted, diversified, and utterly unchallenged in their dominance, continue their reign. But the cooling is coming. Antarctica is drifting south, and the greatest transformation in Cenozoic history is about to begin. There is a moment, not a human moment, not something you could witness from a hilltop or record with an instrument, but a geological moment spread across 1 million years, when the Earth's climate crosses a threshold and the rules of the game change entirely. In our timeline, it happened approximately 34 million years ago, at the boundary between the Eocene and the Oligocene. In this alternate timeline, it happens too because the forces responsible owe nothing to biology. They are purely tectonic, purely oceanic, and as indifferent to the creatures inhabiting the planet's surface as the rotation of the Earth is to the dreams of those sleeping upon it. Antarctica separates from South America. The Drake Passage opens. Cold water, no longer deflected northward by the South American land bridge, begins to circulate freely around the Antarctic continent. The Antarctic Circumpolar Current, the most powerful ocean current on the modern Earth, moving roughly 140 million cubic meters of water per second, a river of cold encircling the bottom of the world. The effect is devastating in its simplicity. Antarctica, now thermally isolated by a ring of cold water, begins to cool. Precipitation that once fell as rain now falls as snow. Snow accumulates. Ice sheets form. First in the highlands of East Antarctica, then spreading, thickening, reflecting more sunlight, cooling the continent further in a feedback loop that, once initiated, becomes self-reinforcing. Within a few million years, Antarctica transitions from a forested continent, home in our timeline, to possums and southern beech trees, and, in this alternate timeline, to cold-adapted dinosaurs and multituberculates, into the frozen desert it remains today. Global temperatures drop. Sea levels fall as water is locked into continental ice. The warm, equable world of the Eocene gives way to something sharper, more seasonal, more demanding. And on every other continent, the biosphere responds. The most consequential botanical revolution in the Cenozoic is the rise of grasslands. Grasses, family Poaceae, had existed since at least the late Cretaceous. Their phytoliths found in dinosaur coprolites from India, described by Vandana Prasad and colleagues in 2005. But for tens of millions of years, they remained minor players, confined to forest margins and disturbed habitats. The Oligocene cooling changes this. As global temperatures decline and seasonal aridity increases, vast interior regions of the continents become too dry and too fire-prone for closed canopy forest. Grasses, with their basal meristems that allow regrowth after grazing and fire, their C4 photosynthetic pathway that confers advantages in hot, dry, low carbon dioxide conditions, and their rapid reproductive cycles sweep across the mid-latitudes. By the Miocene, roughly 20 to 15 million years ago, open grasslands and savannas dominate the interiors of North America, South America, Africa, and Central Asia. In our timeline, this grassland revolution fueled the great mammalian radiations. Horses evolved high-crowned teeth and elongated limbs for running. Bovids, antelope, and deer diversified into hundreds of grazing species. And the predators that hunted them, canids, felids, hyenids, evolved the cursorial body plans we associate with modern plains predators. In this alternate timeline, the mammals are still small. The grasslands still emerge. And the dinosaurs must fill the roles that mammals filled in our world. The hadrosaur descendants are, in many ways, pre-adapted for this moment. Their dental batteries, those remarkable grinding surfaces composed of hundreds of interlocking teeth, continuously replaced throughout life, were already capable of processing tough, fibrous plant material in the late Cretaceous. Now, facing the silica-rich, abrasive foliage of grasses incorporate opaline silica phytoliths into their leaves, a defense against herbivory that wears down teeth with extraordinary speed. The hadrosaur lineage undergoes an intensification of its existing dental strategy. Teeth become even more tightly packed, enamel thickens, replacement rates accelerate. Over 15 million years, the hadrosaur descendants evolve into the dominant, large-bodied grazers of the open plains. Herds of thousands, perhaps tens of thousands, moving across the grasslands in seasonal migrations that track the rainfall, their complex nasal crests producing low-frequency calls that carry across kilometers of open terrain. These are not the hadrosaurs of the Cretaceous. 66 million years of evolution have reshaped them. Their bodies are more robust, their legs proportionally longer relative to their torsos. An adaptation for sustained locomotion across open ground, convergent with the limb proportions of modern ungulates. Some lineages have become fully quadrupedal, their forelimbs thickened and weight-bearing, their posture shifting from the semi-bipedal stance of their ancestors to something more analogous to a rhinoceros or a bison. Others retain bipedality, using their height advantage to scan for predators across the flat terrain, their forelimbs freed for display or for manipulating vegetation. The ceratopsians follow a parallel trajectory. In the late Cretaceous, ceratopsians were already among the most successful herbivorous dinosaurs. Their shearing dental mechanisms efficient at cropping low vegetation, their herding behavior providing safety in numbers. On the Oligocene and Miocene grasslands, ceratopsian descendants diversify into a range of body plans. Massive, rhinoceros-like forms with reduced frills and thickened horns, optimized for defense against the large predators of the plains. Smaller, more agile forms with elongated limbs, filling niches analogous to modern antelope. And heavily armored forms, convergent with ankylosaurs in their defensive strategy. Their frills expanded and fused into continuous bony shields. And the predators? The Tyrannosaur lineage, 66 million years removed from Tyrannosaurus rex, has not stood still. On the open plains, the selective pressure is clear. Pursue large, fast-moving prey across flat terrain with no cover. The tyrannosaur descendants of the Miocene are not the ambush predators of the Cretaceous forest margins. They are cursorial hunters, longer-legged, lighter-bodied, their massive skulls somewhat reduced in proportion, though still formidable, their binocular vision honed to an almost preternatural sharpness by 66 million additional years of selective refinement. Some lineages hunt in pairs or family groups, a social strategy convergent with modern wolves, coordinating their attacks on the flanks of ceratopsian herds with a sophistication that implies, though it does not prove, significant cognitive complexity. But the tyrannosaurs are not alone. The dromaeosaurid descendants, those versatile mid-sized predators, have also adapted to the grasslands. In the open terrain, they have evolved into pack hunters of extraordinary efficiency. Lighter, faster, more numerous than the tyrannosaur descendants, targeting smaller prey and juveniles, harassing the edges of herds, exploiting the confusion of stampedes. Their sickle claws, once used for pinning small prey, have been repurposed for slashing attacks on larger animals. A hunting strategy convergent with the cooperative techniques of African wild dogs, where multiple small predators inflict cumulative damage on prey many times their individual size. In the higher latitudes, the story is different. As temperatures drop through the Oligocene, the dinosaurs of the polar regions face a challenge that their Mesozoic ancestors rarely encountered. True, sustained cold. The fossil record from our timeline already tells us that dinosaurs lived in polar regions during the Cretaceous. The rich dinosaur assemblages of the North Slope of Alaska and the Dinosaur Cove site in southeastern Australia demonstrate that dinosaurs endured months of polar darkness and near-freezing temperatures. But the Oligocene and Miocene cooling pushes beyond this. Winter temperatures at high latitudes drop well below freezing. Snowfall persists for months. Bergmann's rule, the empirical observation that within a broadly distributed taxon, populations in colder climates tend toward larger body size, because larger bodies have a lower surface area to volume ratio and thus lose heat more slowly, operates here with full force. The polar dinosaurs of the Oligocene are giants even by dinosaurian standards. Ceratopsian descendants in the high latitudes evolve thick, subcutaneous fat layers, a convergence with modern marine mammals and Arctic terrestrial species, and dense coats of filamentous integument. This is not speculation. We know from fossil evidence that many dinosaur lineages possessed filamentous body coverings, protofeathers, dino fuzz, structures homologous with avian feathers. In the cold-adapted lineages, these structures become denser, longer, more insulating. The image is startling. Ceratopsians the size of mammoths, their massive bodies blanketed in thick, shaggy coats of feathery down, their breath steaming in the winter air as they scrape through snow to reach the frozen grasses beneath. The world is colder now, sharper, more seasonal. The languid greenhouse of the Mesozoic is gone, replaced by a planet of contrasts. Scorching tropical plains, frozen polar tundra, and everything between. And on every surface, in every biome, the dinosaurs have adapted, diversified, and held their ground. The mammals remain in the shadows, larger than in the Cretaceous, some now the size of a fox or a small dog, exploiting nocturnal niches and burrowing habitats that the dinosaurs cannot efficiently occupy, but still fundamentally constrained. Still waiting for an opening that, in this timeline, never comes. The Miocene stretches forward. The Himalayas continue to rise. The grasslands continue to expand. And somewhere, on a cooling planet, in a dense forest canopy far from the open plains, a small arboreal troodontid descendant wraps its grasping fingers around a branch, tilts its enormous eyes toward the fading light, and listens. 5 million years before the present. The world has been cooling for 30 million years. A long, uneven descent from the greenhouse warmth of the Eocene, punctuated by brief reversals and false springs, but trending inexorably downward. The Antarctic ice sheet is now a permanent feature, kilometers thick, locking away enough water to lower global sea levels by dozens of meters. The Arctic, not yet fully glaciated, is nonetheless cold enough for seasonal sea ice. The temperature gradient between equator and pole has steepened dramatically, driving stronger atmospheric circulation, fiercer storms, and more pronounced seasons. The planet is recognizably modern in its broad climatic architecture, but not yet in its extremes. Those extremes are coming, and before they arrive, the Mediterranean dies. The Messinian salinity crisis, one of the most extraordinary geological events of the last 10 million years, begins approximately 5.96 million years ago, when tectonic movements progressively restrict the connection between the Atlantic Ocean and the Mediterranean basin. The Strait of Gibraltar, or rather the gateway that precedes it, narrows and shallows. Atlantic inflow diminishes flow. The Mediterranean, a nearly enclosed sea losing far more water to evaporation than it receives from rivers, begins to shrink. Over the course of several 100,000 years, in a series of desiccation refilling cycles, the Mediterranean basin transforms from a deep ocean into a chain of hypersaline lakes and vast salt flats. Its floor in places more than 3 kilometers below the surrounding continental surfaces. The evaporate deposits left behind. Layers of salt and gypsum hundreds of meters thick, discovered beneath the Mediterranean seafloor by deep-sea drilling in the 1970s, are the chemical tombstone of a dead ocean. In our timeline, this event reshaped the biogeography of the region, creating land bridges between Africa and Europe, permitting faunal exchange, driving extinctions in marine species adapted to normal salinity, and fundamentally altering the hydrological cycle of the entire Mediterranean borderland. In this alternate timeline, the same event occurs, because it is driven by plate tectonics, not by biology, and its consequences for the dinosaurian world are equally profound. The desiccation of the Mediterranean opens corridors between Africa and Europe that have been closed for millions of years. Dinosaur lineages isolated on the European archipelago, which by the Miocene has consolidated into something approaching its modern geography, though still with significant differences in coastline and island distribution, now encounter African forms for the first time in epochs. The result is a period of intense faunal interchange. European island endemic species, many of them dwarfed by millions of years of insular evolution, suddenly face competition from larger, more generalized African immigrants. Some European endemics go extinct. Others hybridize with their African relatives, producing novel lineages. A few, pre-adapted to the harsh, arid conditions of the desiccating Mediterranean borderlands, expand southward into Africa, exploiting niches that the African forms have not fully occupied. The Messinian also reshapes the salt and mineral chemistry of the surrounding landscapes. The exposed Mediterranean basin, a hellscape of salt flats and evaporate deserts, is one of the most inhospitable environments on the planet's surface. Temperatures in excess of 80 degrees Celsius in the deepest depressions, where the adiabatic lapse rate heats the air, an additional degree for every 100 meters of descent below sea level. No large dinosaur can survive there. But, at the margins, in the brackish pools and saline rivers that feed the dying sea, a different ecosystem emerges. Extremophile microbial communities, salt-tolerant invertebrates, small hardy vertebrates adapted to osmotic stress. Life, as it always does, finds the cracks. Then, approximately 33 million years ago, the Atlantic breaks through. The Zanclean flood, one of the most cataclysmic hydrological events in Earth's recent history, refills the Mediterranean basin in a geological instant. Estimates suggest that at peak flow, the inrushing Atlantic water may have exceeded 100 million cubic meters per second, 1,000 times the discharge of the Amazon River, a waterfall perhaps several hundred meters high at the breach point, thundering into the empty basin for months or years until the Mediterranean is restored to its approximate modern state. The sound would have been audible hundreds of kilometers away. The local climate would have shifted virtually overnight as a vast body of water returned to a region that had been desert for hundreds of thousands of years. And then comes the Pleistocene, beginning approximately 6 million years ago, the Earth enters a period of cyclic glaciation driven by Milankovitch cycles, slow, predictable variations in the planet's orbital parameters, eccentricity, axial tilt, and precession that modulate the distribution of solar radiation across the surface. The effects are dramatic. Continental ice sheets advance and retreat across the northern hemisphere in roughly 100,000-year cycles, reaching as far south as modern New York and London at glacial maxima, then withdrawing to the Arctic during interglacials. Sea levels swing by over 100 meters. Vast areas of continental shelf are alternately exposed and submerged. The Bering Land Bridge connects Asia and North America during glacial lowstands, permitting faunal exchange across the northern continents. The Sunda Shelf connects Borneo, Java, and Sumatra to mainland Southeast Asia. Britain is a peninsula of Europe, not an island. For the dinosaurs, the Pleistocene ice ages represent the most severe sustained environmental challenge since the PETM, but in the opposite direction. The question is not whether they can dissipate heat, but whether they can conserve it. The answer, written in the Principles of Thermoregulation and validated by the survival of large endotherms in our own Ice Age world, mammoths, woolly rhinoceroses, muskoxen, cave bears, is yes, but at a cost. The cost is specialization. The broadly adapted cosmopolitan dinosaur lineages of the warm Miocene are fragmented by glacial barriers into isolated populations confined to refugia. Ice-free zones in the tropics and subtropics, coastal regions moderated by maritime influence, sheltered valleys in mountainous terrain. During glacial maxima, the habitable range for large-bodied dinosaurs contracts dramatically. The great grassland herds of the mid-latitudes are pushed southward, compressed into smaller territories, subjected to intensified competition and predation. Some lineages go extinct, not in the sudden, simultaneous catastrophe of an asteroid impact, but in the slow attrition of range contraction, population fragmentation, and genetic bottlenecking that characterizes background extinction during climate oscillations. But other lineages thrive. The polar adapted forms, those shaggy, massive ceratopsians and thick-feathered theropods that evolved during the Oligocene cooling, now come into their own. They are the megafauna of the glacial world, browsing on tundra vegetation at the edges of ice sheets, migrating seasonally across vast distances, their physiology fine-tuned by 30 million years of cold adaptation to endure conditions that would kill their tropical relatives in days. In the temperate zones, the glacial-interglacial cycles drive rapid evolutionary turnover. Each glacial advance isolates populations. Each interglacial reconnects them. The result is a pulse of speciation and extinction, repeated every 100,000 years, that generates enormous diversity over the course of the Pleistocene. Dinosaur species in the alternate Pleistocene are more numerous, more specialized and more regionally distinct than at any previous point in the post-Cretaceous history. A pattern directly analogous to the mammalian megafaunal diversity of the real Pleistocene, which produced mammoths and giant ground sloths and saber-toothed cats not in spite of the ice ages but because of them. The climatic oscillations, by repeatedly fragmenting and reconnecting populations, act as an engine of diversification. The land bridges, too, play their role. During glacial low stands, the Bering connection allows Asian and North American dinosaur faunas to mix, just as it permitted the exchange of mammoths, bison, and humans in our timeline. South America, connected to North America by the Isthmus of Panama since roughly 3 million years ago. The Great American Interchange, a tectonic event independent of biology, receives an influx of northern dinosaur lineages that compete with and partially displace the endemic South American forms. The result is a homogenization of the global dinosaur fauna at the family level, even as species-level diversity remains high. By the time the most recent glacial maximum passes, roughly 20,000 years before the present, in our timeline, the dinosaurian world has been forged, tempered, and refined by 5 million years of the most volatile climate oscillations the Cenozoic has produced. The lineages that survive are the toughest, the most adaptable, the most resilient. They have endured the death of an ocean, the advance and retreat of continental ice sheets, the compression and expansion of their habitable ranges across dozens of glacial cycles. They are not the dinosaurs of the Cretaceous. They are something new, something shaped by the same forces that shaped mammoths and wolves and eagles in our world. They are the inheritors of a planet that tested them relentlessly and found them sufficient. The Holocene, if one can call it that in a world without humans to name it, begins. The ice retreats, the grasslands expand. And across the warming plains of every continent, the dinosaurs emerge from their glacial refugia, spreading outward into a world that is, for the moment, generous. The alternate present is about to arrive. Open your eyes. You are standing on a ridge of weathered sandstone, somewhere in the interior of what would be, in another history, the North American Great Plains. The latitude is approximately 40 degrees north. The season is late spring. The air is warm, warmer than the same latitude in our world, because the Holocene interglacial in this timeline lacks the residual cooling influence of a recently deglaciated northern hemisphere, scarred by human-driven deforestation and agriculture. The sky is enormous, pale blue, scoured clean by a steady wind that carries on it the scent of crushed grass and something else, something musky, organic, vast, the smell of a living herd. Look south. The grassland stretches to the horizon without interruption. A sea of green and gold, rippling in the wind, punctuated by scattered stands of deciduous trees clustered along waterways. And moving across it, perhaps 3 kilometers distant, but visible as a dark, shifting mass against the pale grass, is a herd of neo-hadrosaurs. They are magnificent. The largest individuals stand perhaps 5 meters at the shoulder, smaller than the great sauropods of the Mesozoic, but larger than any terrestrial mammal in our timeline except the most extreme proboscideans. Their bodies are barrel-shaped, carried on powerful columnar hind legs, their tails held stiffly behind them as dynamic counterbalances, their forelimbs. In this lineage, the fully quadrupedal planes, grazers, thickened into weight-bearing pillars terminating in broad, hoof-like unguals. Their heads are their most striking feature. The nasal crests of their Cretaceous ancestors have, over 66 million years, elaborated into extraordinary structures. Hollow, bony, resonating chambers that extend backward over the skull in sweeping curves. Each species with a distinctive crest shape, each shape producing a distinctive call. The sound they make carries across the plains like the deepest note of a cathedral organ. A subsonic rumble felt in the chest before it is heard by the ear, a frequency low enough to propagate for kilometers through open air and even through the ground itself, a communication strategy convergent with the infrasonic calls of modern elephants, documented by Caitlin O'Connell Rodwell and colleagues in their studies of seismic signaling in Loxodonta africana. The herd numbers perhaps 8,000 individuals. They move in a loose, flowing formation, not the rigid columns of a military march, but the organic, self-organizing pattern of a murmuration, each animal maintaining a roughly constant distance from its neighbors, the whole group shifting direction in response to subtle cues. A change in wind direction, the alarm call of a peripheral sentry, the scent of water. Juvenile neo-hadrosaurs, perhaps a quarter the size of the adults, move near the center of the herd, shielded by the sheer mass of the surrounding bodies. Their crests are undeveloped, smooth, rounded nubs that will not reach full size until sexual maturity, a growth pattern that serves both as an honest signal of age and fitness, and as a mechanism for acoustic differentiation between juveniles and adults. They are grazing, their dental batteries, the evolutionary inheritance of their Cretaceous ancestors, refined and intensified over 66 million years of co-evolution with silica-laden grasses, are biological grinding machines of staggering efficiency. Each individual possesses upward of 1,000 functional teeth arranged in tightly packed magazines, the worn surfaces continuously replaced from below, the enamel differentially hardened to create self-sharpening ridges that slice through the toughest grass stems. The wear rate is ferocious. Each tooth lasts perhaps a few weeks before being shed and replaced. But the supply is, for practical purposes, inexhaustible. It is a dental strategy that no mammal has ever matched, and that the hadrosaur lineage perfected in the Cretaceous and has been honing ever since. Now, shift your gaze west toward the low hills that mark the boundary between the open grassland and the broken terrain of what would be, in our geography, the eastern foothills of the Rockies. There, partially concealed by the topography, something is watching. A pair of neo-tyrannosaurs. They are not the squat, massive bone crushers of the Cretaceous. 66 million years of adaptation to pursuit predation on open grasslands has reshaped them. They are taller, proportionally leaner, their legs longer relative to their body length, their feet more digitigrade. Up on their toes, the metatarsals elongated in a manner convergent with the cursorial adaptations of modern retites and extinct terror birds. Thomas Holtz's work on tyrannosaurid locomotion, published in the early 2000s, already identified the arctometatarsalia foot, a specific arrangement of the metatarsal bones that confers a mechanical advantage for efficient long-distance locomotion, as a key adaptation in the tyrannosaur lineage. In the alternate timeline, this adaptation has been pushed further by 66 million additional years of selective pressure for speed and endurance. Their skulls remain formidable, deep, heavily muscled, the jaw articulation designed for a bite force that, while perhaps reduced from the bone-crushing extremes of T-Rex, is still sufficient to dispatch any prey on the plains. But it is their eyes that would strike an observer most forcefully. Tyrannosaurid binocular vision, the forward-facing eyes that gave T-Rex a stereoscopic visual field rivaling that of modern hawks, has been refined to an extraordinary degree. These animals can detect movement at distances that would challenge the resolution limits of the best mammalian visual systems. They do not need to be close to their prey. They simply need to see it and to wait. They hunt in pairs. A bonded male and female, the female perhaps 15% larger than the male, a sexual dimorphism consistent with the pattern observed in many modern predatory birds and some theropod fossils. Their strategy is not the high-speed sprint of a cheetah, which burns out in seconds. It is the relentless, energy-efficient pursuit of a persistence hunter, a strategy used by African wild dogs and, uniquely among primates, by human endurance runners. They select a target at the periphery of the herd. They begin to follow. Not at full speed, at a steady, ground-covering trot that their cursorial limbs and efficient respiratory system, theropods like modern birds, almost certainly possessed a system of air sacs that permitted unidirectional airflow through the lungs, a far more efficient gas exchange mechanism than the tidal ventilation of mammalian lungs can sustain for hours. The target, a juvenile perhaps, or an older individual with a slight limp, cannot maintain this pace indefinitely. The herd, which cannot afford to slow its migration for one individual, moves on. The gap between the target and the herd widens, and the pair of neo-tyrannosaurs, patient as geology, close the distance. The kill, when it comes, is swift. The lead hunter, the female, accelerates into a final burst, her jaws clamping onto the prey's neck or flank, with a force sufficient to crush vertebrae. The male arrives seconds later, stabilizing the carcass. The feeding begins. But the tyrannosaurs are not the only predators on these plains. Scan the grass more carefully. Lower, closer to the ground, there. A ripple of movement in the tall stems, perhaps 200 meters from the feeding pair. A pack of neo-dromaeosaurids, 10 or 12 individuals, each roughly the size of a large wolf, their bodies low and lean, their feathered arms folded tight against their flanks, their sickle claws retracted for silent movement. They are not here to challenge the tyrannosaurs. They are here to scavenge, to steal a share of the kill once the larger predators have eaten their fill, or to exploit the chaos of a hunt to snatch an unguarded juvenile from the herd's periphery. These dromaeosaurid descendants are pack hunters of remarkable sophistication. Their social structure, inferred in our thought experiment from the comparative biology of modern cooperative hunters like wolves, wild dogs, and Harris's hawks, involves coordinated roles, flankers that drive prey toward ambush positions, sentries that watch for competing predators, and a dominant breeding pair that leads the group's movements. Their vocalizations are complex, a repertoire of whistles, barks, and low-frequency growls that encode information about threat level, prey location, and individual identity. And above it all, riding the thermals that rise from the sun-warmed grasslands, a shape circles. Enormous. A wingspan of 9 meters. Reduced from the 11-meter extremes of Quetzalcoatlus, but still dwarfing any living bird. An Ajdarchid descendant, one of the last of the pterosaur lineages, its wings broad and membranous, its long neck folded in flight, its beak a meter-long spear of keratin and bone. It is a scavenger now, primarily, a soaring sentinel that patrols the plains for carcasses, using its extraordinary visual acuity and its energy-efficient soaring flight to cover hundreds of kilometers in a single day. It has survived 66 million years of avian competition not by outflying the birds, but by being too large, too efficient at soaring, and too specialized in its scavenging niche for the birds to displace. This is the Saurian Serengeti, not a museum diorama, not a theme park fantasy, a living, breathing ecosystem shaped by the same ecological principles that govern the Serengeti of our world: predator-prey dynamics, competitive exclusion, co-evolution, migration, and the relentless calculus of energy acquisition and expenditure. The players are different, the game is the same. And this is only one biome: the forest's weight, the ocean's weight. And in the canopy of the tropical world, something far stranger is taking shape. Leave the plains behind. Travel south and east across the narrowing remnant of the western interior lowlands, past the broadleaf forests of the temperate zone, through the subtropical belt where palms and cycads still flourish in a climate warmer than our own, and into the deep tropics. The equatorial forests that girdle the planet in a band of green so dense, so layered, so ancient in its structural complexity, that the sunlight reaching the forest floor has been filtered through 4 or 5 successive canopy layers and arrives as a dim, greenish twilight, dappled and shifting, more like the light at the bottom of a shallow sea than the light of the open sky. This is the canopy kingdom, and it operates by different rules. On the plains, size is power. Mass means momentum, and momentum means survival. Whether you are a 5-ton ceratopsian deflecting a predator's charge, or a 1-ton tyrannosaur bringing down prey with bone-crushing force. In the canopy, size is a liability. Here, what matters is grip, balance, spatial memory, and the ability to move through a 3-dimensional maze of branches, vines, epiphytes, and aerial roots without falling. The selective pressures are fundamentally different, and they have produced fundamentally different creatures. The dominant arboreal predators of the alternate equatorial forests are the descendants of the small dromaeosaurids and troodontids that retreated into the canopy during the Eocene hothouse 50 million years ago. They have had 50 million years to adapt, and the results are extraordinary. Consider the arboreal troodontids, the lineage we left at the end of Part 5, grasping a branch with oversized eyes in the fading Eocene light. They have changed. Their bodies have shortened, their tails elongated into prehensile balancing organs, not fully grasping like a spider monkey's tail, but stiffened at the base and flexible at the tip, serving as a dynamic counterweight during rapid arboreal locomotion, a function analogous to the tail of a leopard navigating a tree crown. Their hind feet have rotated. The hallux, the first toe, has become partially opposable, gripping branches from the opposite side, a convergence with the foot anatomy of arboreal birds and chameleons rather than primates. Their forelimbs, already semi-grasping in their Cretaceous ancestors, have developed a precision grip, not between thumb and forefinger as in humans and other apes, but between the second and third fingers, with the first finger serving as a stabilizing hook. It is an alien hand. It is also an effective one. Their eyes are enormous relative to their skull, forward-facing, with a binocular overlap exceeding 60 degrees, adapted for judging distances in the complex, cluttered environment of the canopy interior. Their retinas are enriched with rod cells for low light sensitivity, their visual cortex expanded to process the rapid, 3-dimensional spatial information required for brachiation and prey tracking among branches. They see the forest the way a fish sees a coral reef as a volume, not a surface, and their brains. This is where the story becomes most compelling and most speculative, though the speculation is grounded in firm biological principle. The encephalization quotient of the arboreal troodontid descendants has increased significantly over 66 million years. This is not inevitable. Brain tissue is metabolically expensive, consuming roughly 20 times more energy per unit mass than muscle tissue, a cost quantified by Aiello and Wheeler in their 1995 expensive tissue hypothesis. Large brains evolve only when the benefits, improved foraging efficiency, social coordination, predator avoidance, spatial navigation, outweigh the caloric costs. In the canopy environment, those benefits are substantial. Navigating a three-dimensional habitat that changes seasonally, branches grow, break, and regrow, fruiting trees shift their output, competitors rearrange territories, requires a sophisticated cognitive map that must be continuously updated. Locating cryptic prey, insects, small vertebrates, eggs, in a visually cluttered environment rewards pattern recognition and rapid decision-making. And living in social groups, as these arboreal troodontids do, demands the capacity to track social relationships, anticipate the behavior of group members, and negotiate the complex politics of dominance hierarchies and cooperative resource defense. The result is a creature with a brain-to-body ratio comparable to, or perhaps exceeding, that of modern corvids, ravens, crows, jays, which are among the most cognitively sophisticated animals on our planet. Corvids use tools, plan for the future, recognize themselves in mirrors, and solve multi-step problems that challenge human children. The arboreal troodontids of this alternate timeline may possess analogous capabilities, not because they are trying to be intelligent, not because evolution is pushing them towards some human-like pinnacle, but because the ecological pressures they face happen to reward the same cognitive traits that corvid ecology rewards. They use tools, not complex tools, not spears or hammers or levers, but simple extractive tools. Twigs stripped of leaves and inserted into bark crevices to extract insect larvae, a behavior directly analogous to the tool use documented in New Caledonian crows by Gavin Hunt and colleagues. Some populations use stones to crack open hard-shelled seeds or the eggs of arboreal reptiles. Others have been observed. In this thought experiment, remember, we are imagining what a naturalist in this alternate world would document, using leaves as vessels to transport water to cached food sources, a behavior that implies not just tool use, but tool manufacture and planning. They communicate with a repertoire of vocalizations, perhaps 40 or 50 distinct calls, comparable to the communicative complexity of vervet monkeys or prairie dogs, encoding information about predator type, food location, social status, and territorial boundaries. Whether this constitutes language is a question that would occupy the scientists of this world. If this world had scientists, it does not. We will return to this absence. Now shift your attention downward to the mid-canopy and the understory. Here, a different guild of predators operates. The arboreal dromaeosaurid descendants, smaller than their plains-dwelling relatives, perhaps the size of a domestic cat or a small raccoon, are ambush hunters that exploit the vertical dimension. They perch on branches overhanging game trails, their feathered bodies camouflaged in patterns of dappled brown and green that render them nearly invisible against the bark and epiphyte cover, and launch downward onto prey passing below. Small ornithischian descendants, multituberculate mammals, large insects, frogs. Their sickle claws, reduced in size but still functional, serve as anchoring hooks during the initial strike, pinning the prey to the branch while the jaws deliver the killing bite. Above the canopy, the aerial domain belongs to the birds, but not the birds we know. In this timeline, the enantiornithes never went extinct. They remain the dominant arboreal and aerial avian group in the tropics, their toothed beaks and clawed wings persisting as functional features rather than evolutionary relics. The enantiornithine radiation of the Cenozoic has produced an extraordinary diversity of forms. Nectar feeders with elongated curved beaks co-evolved with tropical flowers, seed crackers with heavy parrot-like beaks reinforced by dental ridges, aerial insectivores with wide gapes and bristled facial feathers convergent with modern nightjars, and small, fast-flying pursuit predators that fill the ecological role of hawks and falcons. The neorniths, modern-type birds, are present but subordinate. They dominate in aquatic habitats, waterfowl, shorebirds, waders, and in the open grasslands, ratite-like ground birds, aerial raptors that exploit the open sky where the enantiornithines, adapted to cluttered forest flight, are less competitive. But in the closed canopy, the enantiornithines reign. Their clawed wings, far from being a primitive holdover, prove to be a decisive advantage in the canopy environment, allowing them to cling to trunks and branches in a manner analogous to Huatzin chicks, which use wing claws for climbing in our world, supplementing their flight-based locomotion with a versatile climbing capacity that claw-reduced neornithines cannot match. And the pterosaurs. In the deep forest, they are gone. The Ajdarchid descendants that persist on the open plains cannot operate in the cluttered canopy. Their enormous wingspans require open space for launch and landing. The last forest-adapted pterosaurs, the smaller anurognathids and their relatives, likely succumbed to enantiornithine competition tens of millions of years ago. The canopy is a world of feathers, not membranes. But the forest floor, that dim, humid, root-tangled world beneath the canopy, belongs to a different caste entirely. Here, where the light is too poor for most visual predators, and the terrain too cluttered for speed, the descendants of the Cretaceous ankylosaurs have found their final refuge. Reduced in size from their Mesozoic ancestors, most are now no larger than a wild boar. They are armored omnivores, their bony osteoderms and tail clubs retained as defense against the mid-sized theropods that patrol the understory. They root through the leaf litter for fungi, fallen fruit, invertebrates, and the occasional small vertebrate, their low-slung bodies and short limbs optimized for stability on uneven ground. They are the wild pigs of this world, unglamorous, persistent, ubiquitous. The Canopy Kingdom is not a single ecosystem. It is a vertical city, each floor occupied by different tenants, each governed by different rules, each connected to the others by the endless cycling of nutrients, energy, and predation. From the forest floor to the emergent crowns, life is stacked, layered and interwoven in a complexity that would take a lifetime to catalogue, if anyone were here to catalogue it. The oceans, meanwhile, have been writing their own story, and it is time to listen. Turn away from the land, walk to the edge of the continental shelf, that submerged lip of rock where the shallow coastal waters darken and the seafloor drops away into the blue-black abyss. And look down. The ocean covers 71% of the Earth's surface in this timeline, just as it does in ours, because the volume of water in the hydrosphere is a function of planetary chemistry, not biology. The tides still pulse, the thermohaline circulation still turns, the mid-ocean ridges still spread, and the subduction zones still swallow. But what lives in this ocean, what hunts in its depths and breeds on its shores and migrates across its basins, is profoundly, unsettlingly different. First, a correction, a myth that must be drowned before we proceed. The mosasaurs. Those magnificent marine lizards, the apex predators of the late Cretaceous seas, the ones that popular imagination places alongside the dinosaurs as casualties of the asteroid, were already in decline before the Chicxulub impact. The most recent phylogenetic and stratigraphic analyses suggest that mosasaur diversity peaked in the Campanian stage, roughly 75 to 72 million years ago, and was declining through the Maastrichtian. The reasons are debated. Possible competition with sharks, changing ocean temperatures, reduced habitat as the western interior seaway contracted. In our alternate timeline, the survival of the non-avian dinosaurs on land does not automatically guarantee the survival of the mosasaurs in the sea. Some mosasaur lineages may persist into the Paleocene. The smaller, more generalized forms, perhaps, the ones capable of exploiting coastal and estuarine habitats. But the great open ocean leviathans, the 15-meter Mosasaurus and Tylosaurus, were likely on their way out regardless. This matters because it means the oceans of the alternate Cenozoic are not simply the Cretaceous seas plus 66 million years. They are something else entirely, shaped by the same tectonic and climatic forces that shaped our oceans, but populated by lineages that took different evolutionary paths, because the starting conditions were different. Begin with the crocodilomorphs. In the late Cretaceous, several crocodilomorph lineages were fully or semi-marine. Dinosaurs, a long-snouted form from the Paleocene and Eocene of Africa and South America, one of the few crocodilomorph lineages that survived the actual Cretaceous-Paleogene extinction in our timeline, was a coastal marine predator, perhaps ecologically analogous to a modern saltwater crocodile but more committed to open water. In the alternate timeline, where the end Cretaceous extinction does not occur, the marine crocodilomorphs face no bottleneck. They diversify. Over the Paleocene and Eocene, freed from competition with declining mosasaurs and unopposed by the marine mammals that in our timeline would eventually produce whales and seals, the marine crocodilomorphs undergo an adaptive radiation into pelagic waters. The results after 66 million years are startling. Imagine a fully pelagic crocodilomorph, a descendant of Dinosaurs or a related lineage, that has converged on the body plan of an ichthyosaur or a dolphin. The limbs have transformed into hydrofoil-shaped flippers. The tail has developed a vertical or horizontal fluke for sustained propulsion. The snout has elongated into a narrow, tooth-lined rostrum for catching fish and cephalopods. The body is streamlined, the osteoderms reduced or lost entirely to minimize drag. The lungs, already efficient in crocodilomorphs, have been supplemented by physiological adaptations for deep diving. Increased myoglobin in the muscles for oxygen storage, collapsible rib cages to withstand pressure, slowed heart rates during submersion. This is not fantasy. It is convergent evolution operating on a viable substrate. Crocodilomorphs have re-evolved aquatic and semi-aquatic body plans multiple times in their evolutionary history. Thalattosuchians in the Jurassic, Dinosaurids in the Paleocene, and the physical and physiological changes required for full pelagic life, while extreme, are within the demonstrated evolutionary capacity of the clade. These neo-thalattosuchians, let us call them that, borrowing the name of their Jurassic predecessors, would occupy the ecological niches that in our timeline were filled by toothed whales, mid-sized to large marine predators hunting fish, squid, and other marine vertebrates in open ocean habitats. Some lineages specialize in deep diving, their eyes enlarged for the lightless depths, their echolocation, if it evolves, and there is no guarantee that it would, since echolocation requires specific anatomical preconditions in the nasal passages or larynx that crocodilomorphs may or may not develop, replaced by other sensory modalities. Electroreception, perhaps. Sharks and rays use electroreceptive organs, ampullae of Lorenzini, to detect the bioelectric fields of prey in murky water. Some fish lineages have independently evolved analogous systems. There is no fundamental barrier preventing a marine reptile from developing electroreception, particularly if it hunts in low-visibility deep-water environments where visual and acoustic cues are limited. Now, consider the other marine lineage with deep Mesozoic roots, the plesiosaurs. In our timeline, the plesiosaurs went extinct at the Cretaceous-Paleogene boundary, along with the non-avian dinosaurs and the pterosaurs. But unlike the mosasaurs, the plesiosaurs showed no clear signal of pre-extinction decline. The elasmosaurids, long-necked plesiosaurs, were diverse and apparently thriving in the late Maastrichtian. Had the asteroid not struck, they might well have persisted. In the alternate timeline, the elasmosaurids and their short-necked relatives, the pliosauroids, survive into the Paleocene and face the same Cenozoic ocean changes that all marine organisms must navigate. The closing of the Tethys, the opening of the Southern Ocean, the cooling of deep waters, the restructuring of global ocean circulation. The elasmosaurids, with their distinctive long necks and small heads, were likely ambush predators in productive shallow seas, using their necks to strike at fish from below or from the side, while their large bodies remained relatively stationary, a hunting strategy proposed by Leslie Noe and colleagues. As the Cenozoic oceans cool and the shallow epicontinental seas of the Cretaceous contract, the elasmosaurids must adapt or decline. Some lineages shift to open ocean pelagic habits, their necks shortening over millions of years, as the selective advantage of the ambush strategy diminishes in deep, open water. Others retreat to productive coastal upwelling zones, the cold, nutrient-rich waters along the western margins of continents, where prey density remains high enough to support their energetically expensive body plan. The pliosauroids, the short-necked, large-headed, powerful-jawed marine reptiles, are the ones most likely to evolve into the apex predator role in the alternate oceans. Think of them as the orcas of this world, a pleosauroid descendant with a body length of 12 to 15 meters, a skull 2 meters long, and a bite force sufficient to crush the shells of giant sea turtles, and the bones of smaller marine reptiles, would be a formidable top predator in any ocean basin. Their four-flipper locomotion, unique among marine vertebrates, and biomechanically analyzed by Luke Muscat and colleagues using computational fluid dynamics, provides extraordinary maneuverability, the front flippers generating thrust and the rear flippers providing steering and braking. Over 66 million years of refinement, this propulsion system could be optimized to a degree of hydrodynamic efficiency approaching that of cetaceans. And then there are the spinosaurids. Spinosaurus aegyptiacus, the largest known theropod, was already semi-aquatic in the Cretaceous. Nizar Ibrahim's 2014 and 2020 papers in Science and Nature described a paddle-like tail, reduced hind limbs, dense bones for ballast, and a crocodilian-like snout equipped with conical teeth adapted for catching fish. While Spinosaurus itself was a Cenomanian species, extinct long before the Maastrichtian, the Spinosaurid family persisted into the late Cretaceous in some regions, and the ecological niche of a large, semi-aquatic theropod was clearly viable. In the alternate timeline, Spinosaurid descendants, or other theropod lineages that independently evolve semi-aquatic habits, as convergent evolution would predict in the absence of competing marine mammals, could gradually transition from freshwater and estuarine habitats to fully coastal and eventually pelagic lifestyles. The image is arresting. A theropod dinosaur, 15 meters long, its legs reduced to stabilizing fins, its tail broadened into a propulsive surface, its snout lined with interlocking conical teeth, cruising the continental shelves of the alternate present, like a crocodilian reimagined by the sea itself. It is not a mosasaur. It is not a whale. It is something that has no name in our taxonomy because nothing like it has ever existed in our world. The alternate oceans are not empty of familiar forms. Sharks persist, as they have persisted through every mass extinction in the last 400 million years, their cartilaginous skeletons and flexible life histories rendering them nearly unkillable as a group. Bony fish diversify, filling the countless small-bodied niches that no large marine reptile can efficiently exploit. Sea turtles, survivors in both timelines, continue their ancient migrations. And seabirds, neornithine birds, the one avian clade that dominates open water habitats even in this timeline, patrol the surface, diving for fish and squid, nesting on remote islands, their ecology largely unchanged from our world because their niche has no marine reptile analogue. But below the waves, where the light fails and the pressure mounts and the water turns cold and black, the thrones are occupied by different monarchs, not mammals, not fish. Reptiles, ancient in their lineage, modern in their form, shaped by the same ocean that shaped our whales and our seals, but answering its demands with a different anatomy, a different physiology, a different evolutionary grammar. The ocean does not care what breathes in its depths. It only asks that what lives there can survive. Every world, given enough time, produces its monsters. Not in the storybook sense, not as violations of natural law, but as organisms so improbable, so counterintuitive in their strategies, that encountering them forces a recalibration of what one considers possible. Our world has the anglerfish, which fuses its mate permanently into its own flesh. It has the parasitic wasp, which lays its eggs inside a living caterpillar and chemically reprograms the host's behavior to serve as bodyguard for the developing larvae. It has the naked mole rat, a mammal that lives like a termite, eusocial, functionally immortal by rodent standards, apparently resistant to cancer through mechanisms involving high molecular mass hyaluronan, as documented by Vera Gorbanova and colleagues at the University of Rochester. The alternate world, with its 66 additional million years of dinosaurian evolution, has had precisely as much time to produce its own paradoxes. And the raw material, the theropod body plan, the ornithischian toolkit, the crocodilomorph versatility, is, if anything, more fertile ground for biological strangeness than the mammalian template that produced our world's oddities. Let us catalogue the improbable. Begin underground. Beneath the grasslands of the alternate mid-latitudes, in the deep, moist soils that accumulate in floodplains and river valleys, a lineage of small ornithischian descendants, derived perhaps from the hypsilophodontids or the thescelosaurs of the late Cretaceous, those modest, unassuming herbivores that rarely feature in anyone's imagination of the Mesozoic, has evolved a lifestyle that no dinosaur was ever supposed to adopt. They are burrowers, not casual burrowers, not animals that dig shallow scrapes for nesting, though Cretaceous dinosaurs did this too, as evidenced by the burrowing ornithopod Oryctodromeus cubicularis, described by David Verricchio and colleagues in 2007. These are obligate fossorial organisms, spending the majority of their lives underground in complex tunnel systems that extend for hundreds of meters and penetrate several meters below the surface. Their bodies have been reshaped by the demands of subterranean life. Their limbs are short, powerful, equipped with broad, flattened claws for digging. Their skulls are wedge-shaped, reinforced for use as a ramming tool to compact soil. Their eyes are reduced, not vestigial, but small, adapted for the minimal light that penetrates the tunnel entrances. Their integument, has changed. The feathery covering of their ancestors has been replaced, over millions of years, by a short, velvety pelt of modified filaments that lies flat against the body and does not impede movement through tight spaces, convergent with the fur of moles and golden moles in our world. And here is the paradox. They are eusocial. Eusociality, the division of a colony into reproductive and non-reproductive castes, with cooperative brood care and overlapping generations, is among the rarest and most complex social organizations in the animal kingdom. In our world, it is found in the Hymenoptera, ants, bees, wasps, in termites, in 2 species of shrimp, in 1 species of beetle, and in precisely 2 species of mammal, the naked mole rat and the Damaraland mole rat. The conditions that favour its evolution, as theorised by William Hamilton and elaborated by E. O. Wilson, include high relatedness among colony members, the defensibility of a shared resource, typically a nest or food source, and high ecological costs of independent reproduction. The fossorial ornithischians of the alternate timeline meet all 3 conditions. Their tunnel systems represent an enormous investment of labour, a shared resource that no individual could construct alone. The underground environment is defensible. Tunnel entrances can be blocked, intruders can be repelled in narrow passages where size advantage is neutralised. And the surface is dangerous, patrolled by theropod predators against which a small herbivore has little defence except to never be seen at all. The cost of leaving the colony to breed independently is, quite literally, potentially fatal. The colony structure that emerges over millions of years of selection for cooperative behaviour is organised around a single breeding female. A queen, in functional terms, though she looks nothing like an insect queen. She is the largest individual in the colony, her body swollen with the physiological demands of near-continuous egg production. Non-breeding workers maintain the tunnels, gather roots and tubers from underground caches, and tend the eggs and hatchlings. Soldier caste individuals, larger and more heavily built than workers, guard the tunnel entrances. The parallels with naked mole rat colonies are striking, and they arise not from shared ancestry, but from shared ecological logic. Convergent evolution at the level of social organization. Now, move to the tropics, deep in the equatorial forests where the canopy blocks 90% of incoming sunlight. Another paradox creature has evolved. It is a small theropod, a dromaeosaurid descendant, perhaps 30 centimeters long, slender, its body covered in dark, iridescent feathers. It is, as far as any observer could determine, unremarkable. Until night falls. In the darkness, the animal's chest begins to glow. Bioluminescence, the production of light through chemical reactions, typically involving a luciferin substrate and a luciferase enzyme, has evolved independently more than 50 times in the history of life, in organisms ranging from bacteria to fish to fungi to beetles. The chemistry is well understood. The ecological functions are varied, attracting prey, signaling to mates, warning predators, camouflaging against the dim glow of the surface ocean viewed from below. In terrestrial vertebrates, bioluminescence is exceedingly rare. It is known only in a few species of fish that spend time on land and, arguably, in certain geckos that fluoresce under ultraviolet light. But there is no fundamental biochemical barrier preventing a terrestrial vertebrate from evolving bioluminescence. The genetic machinery for producing luciferase-like enzymes exists in scattered form across many animal lineages. It requires only the right selective pressure to assemble it into a functional, light-producing organ. In the perpetual twilight of the alternate equatorial forest floor, the selective pressure is sexual selection. The bioluminescent dromaeosaurids use their light, produced by modified skin cells in the chest and throat, biochemically derived from dietary luciferin precursors obtained from bioluminescent fungi and insects in the leaf litter, as a mating display. Males with brighter, more sustained or more complexly patterned glows attract more mates. The display is honest. It requires metabolic resources, healthy tissue, and access to luciferin-rich food sources, all of which correlate with individual fitness. It is in essence the same signaling logic that drives the peacock's tail or the bowerbird's elaborate nest constructions. A costly, conspicuous advertisement of genetic quality. The glow is faint by human standards. Comparable to a large firefly, perhaps, visible only in near-total darkness. But in the lightless understory of a forest where the canopy is so thick that the forest floor receives less illumination than a moonlit night, it is a beacon. During the breeding season, the forest floor at night shimmers with dozens of points of soft, blue-green light, each one a small theropod, advertising its presence to potential mates. Now consider venom. In our world, venomous reptiles are common. Snakes, the Gila monster, some monitor lizards. In the Cretaceous, there is disputed evidence that at least one dinosaur lineage may have been venomous. Sinornithosaurus, a small dromaeosaurid from the early Cretaceous of China, was described by Enpu Gong and colleagues in 2009 as possessing grooved teeth and what appeared to be a venom delivery apparatus in the upper jaw, though this interpretation remains controversial and has been challenged by subsequent studies. Set aside the question of whether Sinornithosaurus was actually venomous. The relevant point is that the anatomical precursors for venom delivery, grooved or hollow teeth, modified salivary glands capable of producing toxic secretions, exist within the theropod bioplan. Given 66 million additional years of evolution, the probability that at least one theropod lineage evolves a functional venom system approaches certainty. In the alternate present, venomous theropods occupy a specific niche, small-bodied ambush predators in environments where prey is large relative to the predator's size and must be subdued quickly. The venom, a cocktail of hemotoxins and neurotoxins convergent with the venom of modern rear-fanged snakes, is delivered through grooved anterior teeth and serves not to kill instantly but to incapacitate, causing rapid loss of muscular coordination in the prey animal. The predator bites, releases, retreats, and follows the envenomated prey until it collapses. It is precisely the hunting strategy of the Komodo dragon, which delivers a toxic bite and then tracks its weakened prey over hours or days. Though recent research by Brian Fry and colleagues has reclassified the Komodo's weapon as venom rather than septic bacteria, underground eusocialists, bioluminescent forest ghosts, venomous shadow hunters. Each one is paradoxical only in the sense that no dinosaur in our fossil record has achieved these specific strategies. But each one is grounded in demonstrated biological principles, in convergent evolution operating on a theropod or ornithischian substrate, in the relentless creativity of natural selection, given sufficient time and sufficient pressure. The paradox is not that these creatures exist. The paradox is that we find them surprising. We have seen life do all of these things before, in other lineages, on other branches of the evolutionary tree. We simply never imagined that dinosaurs could do them too, because in our world, they were never given the chance. Now we arrive at the question that has haunted this thought experiment since the moment the rock missed. The question that every audience, every reader, every curious mind eventually asks when confronted with a world where dinosaurs persist for 66 million additional years. It is the question that Dale Russell asked in 1982, and the answer he gave has distorted the conversation ever since. The question, Could dinosaurs evolve intelligence? Russell's answer, the dinosauroid, a bipedal, large-brained humanoid creature with forward-facing eyes, manipulative hands, and an upright posture derived from the troodontid body plan, was a provocation dressed as science. It appeared in a paper co-authored with Ron Seguin, accompanied by a life-sized sculpture that looked, to most observers, like a green-skinned human being with reptilian features. The scientific community's response was immediate and largely critical. The dinosauroid was not a prediction grounded in evolutionary principle. It was an exercise in anthropocentrism, the assumption that intelligence, if it evolves, must converge on the human form, because the human form is the only template we have for a technologically capable species. This assumption is wrong, and it is important to understand precisely why it is wrong, because the error illuminates something fundamental about how we think about minds. The human body plan, upright bipedal posture, forward-facing eyes, large cranium, opposable thumbs, is not the cause of human intelligence. It is the context in which one particular form of intelligence evolved. The primate lineage, over 65 million years of arboreal and eventually terrestrial life, developed a specific suite of traits: grasping hands, stereoscopic color vision, extended parental care, social group living, that created the preconditions for encephalization. But these traits are not the only possible preconditions. They are simply the ones that happen to come together in one lineage, on one planet, after one particular mass extinction cleared the ecological space for mammals to diversify. Intelligence, in the broader biological sense, the capacity for flexible, context-dependent behavior that goes beyond pre-programmed instinct, has evolved independently multiple times in our world, and it has never converged on the human form. Consider the corvids. New Caledonian crows manufacture tools from pandanus leaves, trimming them into specific shapes with their beaks and carrying them between foraging sites. They solve multi-step puzzles that require causal reasoning. They remember the faces of individual humans who have threatened them and communicate that information to other crows, as documented by John Marsloff and colleagues at the University of Washington. Their encephalization quotient rivals that of some primates, and they accomplish all of this with a brain structured fundamentally differently from a mammalian brain. Organized around a structure called the nidopallium caudolateral rather than a neocortex, achieving analogous computational results through different neural architecture. Consider the octopus. Octopus vulgaris can open screw-top jars, navigate mazes, recognize individual human faces, and use coconut shells as portable shelters. Behavior that meets the operational definition of tool use. Its intelligence is distributed. Roughly 2/3 of its neurons are located in its arms, not its central brain, creating a cognitive architecture that has no mammalian or avian parallel. It evolved this intelligence on a completely independent trajectory. Cephalopods diverged from the vertebrate lineage over 500 million years ago. The octopus mind is alien in the most literal sense. It is proof that intelligence is not a destination, but a strategy, and that the same strategy can be reached by wildly different routes. Now, apply these principles to the alternate timeline. The troodontid descendants we left in the canopy, the arboreal, large-eyed, tool-using creatures with brains comparable to modern corvids, are the most obvious candidates for advanced cognition. But their intelligence, if it develops, will look nothing like human intelligence, because their bodies are nothing like human bodies, and the problems they solve are nothing like human problems. Their cognitive strengths will be spatial, not linguistic. The demands of arboreal life, navigating a three-dimensional habitat that changes seasonally, remembering the locations of hundreds of food sources across a territory, tracking the movements of competitors and predators in a cluttered visual environment. Select for extraordinary spatial memory and mental mapping. This is the cognitive profile of a Clark's nutcracker, which remembers the locations of up to 10,000 seed caches across a mountain landscape, or a honeybee, which communicates spatial information through the waggle dance. The arboreal troodontids may develop spatial cognition that far exceeds anything a human brain can achieve, while simultaneously lacking the capacity for the kind of abstract, symbolic reasoning that underpins human language and mathematics. Their social intelligence will be Machiavellian, not cooperative in the human sense. Living in small hierarchical groups in a resource-limited canopy environment, they face the same social pressures that the primatologist Frans de Waal documented in chimpanzee societies. The need to form and break alliances, to deceive competitors, to assess the reliability of cooperative partners, and to navigate a shifting landscape of dominance relationships. But they lack the specific evolutionary history that pushed the human lineage toward cumulative cultural transmission. The ratchet effect described by Michael Tomasello, wherein each generation builds on the innovations of the previous one, creating a body of shared knowledge that no individual could independently reconstruct. Cumulative culture, as far as we can determine, requires a conjunction of traits: imitative learning, shared intentionality, externalized symbolic communication that evolved in the hominin lineage under very specific ecological and social conditions. There is no reason to assume that the troodontid descendants will develop this conjunction. They may be brilliant individual problem solvers like crows. They may be sophisticated social manipulators like chimpanzees. But they are unlikely to build civilizations because civilizations require not just intelligence, but a very specific kind of intelligence. One that, in the history of life on Earth, has evolved exactly once. This is a crucial point, and it deserves emphasis. Intelligence is not a ladder. It is a landscape. A vast, multidimensional space of possible cognitive strategies, each one adapted to specific ecological demands, each one trading off certain capabilities for others. Human intelligence is one peak in this landscape, optimized for cumulative cultural transmission, abstract reasoning, and technological manipulation of the environment. Corvid intelligence is another peak, optimized for spatial memory, causal reasoning, and social information processing. Octopus intelligence is yet another, optimized for rapid learning, camouflage control, and distributed sensory-motor integration. None of these is higher or lower than the others. They are different solutions to different problems. The troodontid descendants of the alternate timeline represent yet another peak, one that our world has never seen, because the lineage that might have produced it was extinguished 66 million years ago by an accident of orbital mechanics. Their intelligence is real. It is sophisticated. It enables behaviors, tool use, social coordination, complex communication, flexible problem solving, that would, if observed by a human scientist, provoke admiration and intense study. But it is not human intelligence. It does not produce written language, or agriculture, or mathematics, or telescopes, or the capacity to ask the question, what if the asteroid had hit? And this is perhaps the deepest paradox of this entire thought experiment. In a world where dinosaurs never went extinct, intelligence still evolves. It evolves in multiple lineages, just as it did in our world. It produces creatures of remarkable cognitive sophistication. Creatures that use tools, that communicate complex information, that solve novel problems, that exhibit what any behavioral ecologist would recognize as consciousness, or something very close to it. But it does not produce observers, not in the philosophical sense, not beings capable of reflecting on their own existence, of constructing narratives about the past, of imagining alternative futures. Not beings who would stand on a ridge overlooking the Saurian Serengeti and wonder what the world might have looked like if the asteroid had hit. The troodontid descendant in the canopy cracks a seed with a carefully selected stone, adjusts its grip with its alien three-fingered hand, and looks out across the forest with eyes that see everything and understand nothing about the cosmic accident that made its existence possible. It does not know it lives in an alternate timeline. It does not know what a timeline is. It simply lives. We have spent 12 chapters walking through a world of giants and ghosts, of feathered predators and resonant herds and bioluminescent forest spirits. We have catalogued the wonders of a planet that was never stripped of its ruling dynasty. But there is a silence at the center of this story, a conspicuous absence like a chair left empty at a banquet, and it is time to sit with it. Where are the mammals? They are here. They have always been here. Since the late Triassic, more than 200 million years ago, the mammals and their synapsid ancestors have shared the Earth with the archosaurs. They endured the Triassic-Jurassic extinction. They survived the long Jurassic night of sauropod dominance. They diversified modestly through the Cretaceous, filling the ecological crevices that the dinosaurs left unoccupied. The nocturnal insectivore niche, the small seed-eater niche, the burrowing omnivore niche. They were never absent, they were simply suppressed. This suppression is not a metaphor. It is a measurable, documented phenomenon. In our timeline, the fossil record shows that mammalian body size remained constrained throughout the Mesozoic era. The largest known Mesozoic mammal, Repenomamus giganticus from the early Cretaceous of China, weighed approximately 12 to 14 kilograms, roughly the size of a large domestic cat. For over 150 million years, no mammal exceeded this size ceiling. Then, within 10 million years of the end Cretaceous extinction, mammals had produced species weighing hundreds of kilograms. Within 30 million years, they had produced Paraceratherium, an 18-ton hornless rhinoceros, relative that remains the largest land mammal ever to have lived. The pattern is unambiguous. Dinosaur dominance imposed an ecological ceiling on mammalian body size, and the removal of that ceiling triggered an explosive radiation. In a landmark 2010 study published in Science, Graham Slater and colleagues used phylogenetic comparative methods to demonstrate that the rate of mammalian body size evolution increased dramatically after the Cretaceous-Paleogene boundary. By roughly an order of magnitude, the mammals did not gradually grow larger over the Cenozoic. They erupted. The ecological space vacated by the dinosaurs was filled with a speed and diversity that suggests the mammalian body plan was already pre-adapted for large-bodied niches, but had been prevented from accessing them by competitive exclusion. In the alternate timeline, the exclusion never ends. The mammals of this world are diverse, perhaps more diverse than their Mesozoic ancestors, because 66 million additional years of evolution within their constrained niches has produced considerable specialization. But they are small. The largest mammal on the alternate modern Earth probably does not exceed 20 kilograms, the size of a medium dog. Most are far smaller. They are the mice and shrews and moles and bats of this world, filling the same ecological interstices they filled in the Cretaceous: nocturnal insectivores, subterranean burrowers, arboreal seed-eaters, aerial insect hawkers. The multituberculates, that ancient and spectacularly successful mammalian order that in our timeline went extinct in the Eocene, outcompeted by rodents, may still survive in this alternate world. Without the explosive radiation of rodents, which in our timeline filled virtually every small herbivore niche on every continent, the multituberculates face less competitive pressure. Their blade-like premolars, adapted for slicing seeds and tough plant material, remain an effective dental tool in the niches they have occupied for over 100 million years. They are the rodents of this world. Small, prolific, ubiquitous, and almost invisible beneath the feet of the saurian megafauna. The marsupials and placentals, which in our timeline diverged into the two great mammalian radiations of the Cenozoic, remain in a state of evolutionary détente. Neither group able to achieve the ecological dominance that would allow it to displace the other, because neither group can access the large-bodied niches where competitive displacement is most consequential. In the tropics, small marsupials and placentals coexist, partitioning the nocturnal insectivore niche by microhabitat and prey type. In the temperate zones, placentals may have a slight edge. Their more efficient placental reproduction, which allows longer gestation and more developed neonates, confers advantages in seasonal environments where the window for breeding is short. But the advantage is marginal, and the mammals of both groups remain, by any large-bodied standard, insignificant. There are no primates. This requires a moment of contemplation, because the implications are so total that the mind tends to slide off them rather than absorb them. The primate order, the lineage that produced lemurs, monkeys, apes, and humans, originated in the early Paleocene of our timeline, probably from a small, arboreal, insectivorous ancestor resembling a modern tree shrew. The earliest probable primate, Purgatorius, is known from sediments dating to within a few 100,000 years of the Cretaceous-Paleogene boundary, so close to the extinction event that it is debated whether Purgatorius originated before or after the asteroid impact. In either case, the primate radiation that followed was made possible by the disappearance of the arboreal dinosaurs, the small dromaeosaurids, the troodontids, the enantiornithine birds, that had previously dominated the canopy niches that primates would eventually fill. In the alternate timeline, those arboreal dinosaurs never disappeared. The canopy niches are occupied. The small, nocturnal, insectivorous mammal that might have given rise to the primates remains small, nocturnal, and insectivorous. It does not diversify into frugivorous, folivorous, and omnivorous forms. It does not develop the grasping hands, the binocular color vision, the enlarged brains that characterize the primate order. It remains what it is, a shrew-like creature hiding in the dark spaces between dinosaur territories, eating insects and hoping not to be eaten. There are no monkeys. There are no apes. There is no bipedal hominin walking upright on the African savanna, freeing its hands for tool use, developing language, building fire, painting on cave walls, burying its dead, asking questions about the stars. There are no ungulates, no horses, no cattle, no deer, no antelope. The grazing niches are filled by hadrosaur and ceratopsian descendants. There are no carnivorous mammals, no wolves, no cats, no bears. The predator niches are filled by tyrannosaur and dromaeosaurid descendants. There are no whales, no dolphins, no seals. The marine mammal niches are filled by neothalatosutian, crocodilomorphs, and plesiosaur descendants. There are no elephants, no rhinoceroses, no hippopotamuses. Every large-bodied ecological role that mammals fill in our world is, in this world, filled by a dinosaur or a crocodilomorph or a marine reptile. The entire mammalian Cenozoic, every lineage, every radiation, every iconic species from Smilodon to the blue whale, is compressed into a shadow the size of a rat hiding in a burrow, waiting for nightfall. This is not tragedy in the dramatic sense. The mammals of the alternate timeline are not suffering. They are not aware of what they have lost, because they have lost nothing. They never had it. Evolution does not grieve for paths not taken. Species do not mourn the adaptations they might have developed if circumstances had been different. The small marsupial huddled in its nest hollow, as a dromaeosaurid's footstep shakes, the branch above is not thinking about the fact that, in another universe, its distant relatives rule the planet. It is thinking, if the word applies, about warmth and food and the sound of predators in the dark. But we can grieve, or rather, and this is the edge of the abyss toward which this entire story has been walking, we could grieve if we existed, which in this timeline we do not. The suppression of the mammals is not merely a zoological footnote, it is an existential erasure. Without the mammalian radiation, there is no primate lineage. Without primates, there is no Homo. Without Homo, there is no consciousness of the kind that reflects on its own origins, that asks, "Why am I here?" that constructs elaborate hypothetical scenarios about asteroids that did or did not strike the Earth 66 million years ago. The alternate world is not missing mammals. It is missing witnesses. And a world without witnesses is a world that, in some profound and perhaps unanswerable philosophical sense, does not know it exists. There is a thought experiment in philosophy, older than this one, more venerable and far more disturbing, that asks a question so simple it seems almost childish, until it begins to unravel every assumption one holds about the nature of existence. If a tree falls in a forest and no one is there to hear it, does it make a sound? The standard answer, the physicist's answer, is yes, of course it does. Sound is a compression wave propagating through a medium. It does not require an ear to exist. The tree falls, the air vibrates, the wave propagates, and the forest floor absorbs it. Sound happened. No observer necessary. But there is a deeper version of the question, one that the philosopher George Berkeley posed in the 18th century, and that quantum mechanics has, in its own strange way, resurrected. Does the experience of sound require a listener? Is a compression wave, in the absence of a nervous system capable of transducing it into sensation, meaningfully different from silence? And if the entire universe is a compression wave, a vast, intricate pattern of matter and energy propagating through space-time according to fixed laws, does it mean anything if there is no mind to interpret it? This alternate Earth, this saurian planet of resonant herds and bioluminescent forests and pelagic reptilian leviathans, is Berkeley's forest writ large. It is a world of extraordinary beauty, complexity, and ecological sophistication. It is a world where evolution has produced organisms of remarkable cognitive ability. The arboreal troodontids with their corvid-level problem-solving, the pack-hunting dromaeosaurids with their social intelligence, the enantiornithine birds with their complex vocalizations. But it is a world without what philosophers call second-order consciousness. The awareness of being aware, the capacity to reflect on one's own mental states, to ask questions, to construct narratives, to imagine worlds that do not exist. It is a world without philosophy, without science, without art, without the concept of without. Let us be careful here because the terrain is treacherous. It would be easy, tempting, even natural, to frame this as a loss. To say that the alternate Earth is somehow lesser because it lacks human-type consciousness, that the Saurian Serengeti is diminished because no one paints it, that the canopy kingdoms are incomplete because no one writes poems about them. This framing is itself a form of anthropocentrism, subtler than the dinosauroid fallacy but equally distorting. It assumes that consciousness of the human type is the purpose, or at least the pinnacle of biological evolution. That the biosphere is in some sense aiming at producing observers, and that a biosphere that fails to produce them has failed. Evolution has no purpose. This is not a controversial statement among biologists. It is a foundational principle. Natural selection is a process, not a project. It does not aim at complexity or intelligence or consciousness or any other outcome that humans happen to value. It produces whatever survives, and what survives is determined by local conditions: the climate, the geography, the competitors, the parasites, the 10,000 contingent factors that differ from one time and place to another. In some environments, intelligence is favored. In others, it is irrelevant or even costly. The most successful organisms on Earth by any measure of biomass, diversity, or evolutionary longevity are bacteria. And bacteria have no brains at all. The alternate Earth is not lesser for lacking human consciousness. It is simply different. It is a world where the contingent factors that, in our timeline, favored the evolution of large-brained primates on the African savanna, the disappearance of the dinosaurs, the radiation of mammals, the formation of the East African Rift, the drying of the climate, the expansion of grasslands, the specific ecological pressures that selected for bipedalism, tool use, and social cognition in one particular lineage of ape, did not align. The dominoes did not fall in the right order. The cascade that produced Homo sapiens never initiated. And yet the thought persists, irrational and irresistible. Something is missing. Perhaps what is missing is not consciousness, but witness. The universe, as far as we can determine, has been producing stars and planets and complex chemistry for approximately 13.8 billion years. For most of that time, on most of those worlds, no one has been watching. The supernovae explode, the galaxies collide, the organic molecules assemble and disassemble in warm tidal pools on rocky worlds orbiting yellow stars. And none of it is observed in the sense that a conscious mind registers it, remembers it, and reflects upon it. The universe, in its default state, is unwitnessed. In our timeline, on this one planet, in this one lineage, in the last few 100,000 years, of a 4.5 billion year history, the universe produced a witness, a species capable of looking up at the stars and understanding, however imperfectly, what they are, a species capable of digging into the rock and reading the history of life, written in fossil bone and sedimentary strata, a species capable of asking, "What if?" and following the question across 66 million years of counterfactual history. This is not destiny. It is not purpose. It is accident. The same kind of accident that sent an asteroid toward the Yucatan, the same kind of accident that determined whether a particular mutation would occur in a particular organism in a particular generation. The existence of human consciousness is no more meant to be than the existence of the Chicxulub crater. Both are products of contingency, of the specific and unrepeatable sequence of events that constitutes the history of this particular universe. But contingency does not diminish significance. The fact that something is accidental does not make it meaningless. A sunset is accidental. The specific arrangement of atmospheric particles that produces a particular display of color on a particular evening is the product of chaotic dynamics that no one planned and no one could have predicted. And yet, it is beautiful, and its beauty is experienced by a mind that is itself accidental, a product of the same chaotic dynamics, a pattern of electrochemical activity in a lump of neural tissue that happens by no design and for no reason to be capable of registering beauty. The alternate Earth has sunsets. It has beauty, beauty beyond measure, beauty that would stagger any human who could somehow be transported there to see it. The resonant calls of the neo-hadrosaur herds at dawn, the bioluminescent shimmer of the forest floor at night, the vast, silent glide of an Ajdarkid descendant across a sky unmarked by contrails or satellites. The play of light on the scales of a pelagic pliosauroid breaking the surface of a warm Tethyan sea. All of it unwitnessed, all of it unrecorded, all of it happening in a present that has no past, because no one is there to remember it, and no future, because no one is there to anticipate it. An eternal now experienced by billions of organisms that live entirely in the moment, not by choice, not by spiritual discipline, but by biological limitation. They cannot do otherwise. They do not know that otherwise exists. The philosopher Thomas Nagel, in his famous 1974 paper, What Is It Like to Be a Bat?, argued that consciousness has an irreducibly subjective character, that there is something it is like to be a bat, an experience that cannot be captured by any objective, third-person description of the bat's neurology or behavior. If Nagel is right, then there is something it is like to be a neo-hadrosaur, standing in a herd of 8,000 on a Miocene grassland, calling into the wind with a voice that shakes the ground. There is something it is like to be an arboreal troodontid, cracking a seed in the canopy twilight. There is something it is like to be a pelagic crocodilomorph, diving into the cold dark of the abyssal ocean. But there is no one to ask them what it is like, no one to wonder, no one to write it down. The silence where we should be is not empty. It is full of life, full of experience, full of sensation, full of the raw, unprocessed qualia of billions of organisms living and dying and reproducing across 66 million years of unrecorded history. It is a silence that roars, and it is a silence that, in the deepest and most unsettling sense, is the default. Our world, the world with witnesses, with questioners, with beings who lie awake at night and wonder about dinosaurs, is the exception. The alternate Earth, the Earth of eternal present and unwitnessed beauty, is what the universe normally produces. We are the anomaly, and the anomaly rests on the edge of a rock that fell from space. Pull back, further, further still. Leave the alternate Earth behind, its herds and hunters, its canopy kingdoms and abyssal thrones, its 66 million years of unwitnessed splendor. Leave our Earth behind too, its cities and satellites, its wars and symphonies, its one fragile species that learned to ask questions about its own existence. Pull back until both worlds are indistinguishable. Two pale blue dots orbiting the same yellow star, separated not by space but by the thinnest membrane of probability, by the difference between an asteroid that arrived 6 hours early and one that arrived on time. From this distance, the difference is invisible. The star burns, the planet orbits, the oceans glint. The atmosphere swirls with weather that obeys the same fluid dynamics, regardless of what walks or swims or flies beneath it. The universe does not know which version of Earth it contains. It does not care. It cannot care. Caring requires a nervous system, and the universe, vast, ancient, governed by laws of breathtaking mathematical elegance, has no nervous system. It has only matter, energy, space-time, and the four fundamental forces that choreograph their interactions. This is the insight that deep time offers to anyone willing to sit with it long enough. The universe is not hostile. It is not benevolent. It is not indifferent in the way that a person is indifferent. Choosing not to care, capable of caring, but declining. It is indifferent in a more fundamental sense. It lacks the apparatus for caring. The concept does not apply. Asking whether the universe cares about the existence of consciousness is like asking whether the number 7 is happy. The question is grammatically coherent but ontologically empty. And yet, and this is the paradox that refuses to resolve, the knot at the center of every philosophy of mind and every late-night conversation about the meaning of existence. Here we are, conscious, aware, capable of formulating the question, even if incapable of answering it. The universe produced us, accidentally, contingently, through a chain of causation so long and so improbable that retracing it induces a kind of vertigo. A star exploded and seeded the interstellar medium with heavy elements. A cloud of gas and dust collapsed into a solar system. A planet formed at the right distance from the right star. Chemistry became biology. Biology became complexity. Complexity, after 4 billion years of trial and error, became awareness. And awareness looked back at the process that created it and asked, why? There may be no answer. The question, why, presupposes purpose, and purpose presupposes a purposer, a mind behind the machinery, a designer behind the design. If no such mind exists, if the universe is, as the physicist Steven Weinberg wrote in his 1977 book, The First 3 Minutes, pointless, then the question is not unanswerable but unanswerable in principle. It is a question that dissolves upon close examination, like a mirage that vanishes when you walk toward it. The universe is not pointless in the way that a bad movie is pointless. It is pointless in the way that a mountain is pointless. It simply is. But the human mind, and this may be its most defining characteristic, the trait that separates it most decisively from even the most cognitively sophisticated non-human animals, cannot accept this. It cannot rest in pointlessness. It constructs meaning the way a spider constructs a web. Instinctively, compulsively, out of the raw material of its own experience. It looks at a fossil bone and sees a story. It looks at a crater and sees a turning point. It looks at an asteroid that might have missed and sees an entire alternate history, populated with creatures that never existed, governed by laws that are real and suffused with a beauty that no one in that hypothetical world could ever appreciate. This is what we have been doing for the last 14 chapters. Constructing meaning from contingency. Building a cathedral of speculation on the foundation of a single geological accident. And the cathedral is beautiful, not because it is true, but because it illuminates something true about the relationship between chance and consequence, between the cosmic and the biological, between the indifference of the universe and the stubborn, irrational insistence of consciousness on finding significance in it. The asteroid that struck the Yucatan 66 million years ago was not a gift. It was not a punishment. It was not a narrative device deployed by a storytelling cosmos to clear the stage for the next act. It was a rock. It followed a trajectory determined by gravitational interactions that began billions of years earlier. It struck a planet that happened to be in its path. The consequences, the extinction of the non-avian dinosaurs, the radiation of mammals, the eventual emergence of a species that would name the crater and mourn the dead and wonder what might have been, were not intended. They were not foreseen. They simply happened in the same way that weather happens, in the same way that erosion happens, in the same way that stars are born and die, and the elements they forge are scattered into the void to become, eventually, the bones and brains of creatures capable of contemplating their own mortality. Stephen Jay Gould, the paleontologist and evolutionary biologist whose work did more than perhaps anyone else's to popularize the concept of contingency in evolution, wrote in his 1989 book, Wonderful Life, that if the tape of life were rewound and replayed, the results would be utterly different. Humans would not re-evolve. Intelligence of our specific type would not re-emerge. The history of life is not a deterministic march toward a predetermined goal. It is a branching, pruning, wildly unpredictable process in which each outcome depends on the specific and unrepeatable sequence of accidents that preceded it. Replay the tape with a slightly different Cambrian explosion, and you get a different Ordovician. Replay it with a different Permian extinction, and you get a different Triassic. Replay it with a missed asteroid, and you get the Saurian Earth, magnificent, complex, and empty of anyone who could appreciate its magnificence. Gould's metaphor has been challenged. Simon Conway Morris, in his 2003 book Life's Solution, argued that convergent evolution, the tendency of natural selection to produce similar solutions to similar problems, imposes deep constraints on the space of possible biological outcomes, making certain forms, eyes, wings, intelligence, near inevitable given sufficient time. Perhaps intelligence of some kind would emerge on the alternate Earth, given another 100 million years. Perhaps the troodontid descendants would eventually cross the threshold into second-order consciousness, cumulative culture, and technological civilization. Perhaps. But perhaps is not inevitably, and 100 million years is a long time to wait for a perhaps. What we can say, what the science supports, what the thought experiment illuminates is this: the existence of a species capable of reflecting on its own existence is not a given. It is not a default outcome of planetary evolution. It is a specific, contingent, improbable result of a specific, contingent, improbable sequence of events. A sequence that includes, among its countless links, a rock from the Oort cloud that happened to arrive at precisely the wrong time, at precisely the wrong place, with precisely the wrong energy to end one world and begin another. We are here because the rock hit. The dinosaurs are not here because the rock hit. In the alternate timeline, the dinosaurs are there because the rock missed. We are not there because the rock missed. Neither outcome is better. Neither is worse. Both are real, in the sense that both are consistent with the laws of physics and the principles of biology. The universe permits both. It endorses neither. And this vertiginous, beautiful, terrifying realization is the deepest lesson of deep time. Not that the past is long, though it is. Not that the present is fragile, though it is. But that existence itself, conscious, reflective, wondering existence, is a flicker. A brief, improbable flicker in an ocean of time that stretches, in both directions, toward an infinity that does not notice the flicker and would not mourn its absence. The neo-hadrosaurs call across the plains of the alternate Earth, their subsonic voices shaking the grass. The arboreal troodontids crack seeds in the canopy twilight. The pelagic pliosauroids dive into the cold Pacific dark. The bioluminescent dromaeosaurids shimmer on the forest floor like fallen stars. None of them know we are watching. None of them know that watching is possible. And somewhere, not here, not there, but in the thin, shimmering space between what happened and what might have happened, a rock tumbles silently through the void, carrying on its ancient surface a question that no one in any timeline will ever fully answer. Was it always going to be this way? Or could it, just as easily, have been something else entirely? The rock does not answer. It does not hear the question. It simply falls, obeying gravity toward whatever world is waiting, or not waiting, below. The screen goes dark. The silence holds. And somewhere, in the real world, your world, the one where the rock hit, the one where the mammals rose, the one where a peculiar species of ape learned to tell stories about things that never happened, you are still here, still listening, still wondering. That, in itself, is the most improbable thing of all.